face. Cut my lifeline when drifting through space. I saw an angel, I saw my fate. I can only thank God it was not too late.
Great. Then welcome everyone to the second day of SQA. Today's program, I'll just give you a brief overview of what we'll see today. We'll start with a keynote by Anna Graslino, then we will have more fab talks, coffee break, then we will hear about Fluxonium and error-protected qubits. Then we have a lunch, poster session, workshops, and then we will have quantum algorithms. And at the end, we have excursions. Keep in mind here that in the program it says 6:30, but this is more like a colloquial 6:30. It's more like when we are done here, we will sort of slowly get going to wherever you want to go, depending on which tour you are signed up for. So this 6:30, don't read it too literal. Yes, as before, we have keynote 45 minutes, invited talk 25 minutes, and contributor talk 12 minutes. And you can, as always, find all the abstracts here. And that also goes for the poster session. All the abstracts for the poster session will be also on this page. Yes. Yes. Again, one more comment. I also made that yesterday, but the badges here, remember to wear them at all time. Just a reminder. Today we will actually start to check. So yesterday, because people were still coming in and signing up, it was a little bit more lax. But today the security staff at the entrance will actually ask you for the badge, so just wear it. Today we also have a number of workshops. They will be next door. What will happen is that when the workshop is about to start, some of our volunteers, usually in a white t-shirt, will be there and show you the way, and then you will find your workshop. The poster session happens here on stage. So what will happen is that once we are done with the session, Fluxonium and error-protected qubits, volunteers will very quickly put up the poster session boards, and then just come and hang right away your poster, and then it will happen here over the next 3 hours. Right. Yes, this I also said yesterday, but just a reminder, if you need Wi-Fi, this is the Wi-Fi code at Teater de Veste Wi-Fi. And the info desk, which is here, is open all day, so if you have questions, there. And with that, I want to introduce our first speaker of today, which is Anna Graslino, who is the director of the CMQS Center at Fermilab, where they have done amazing work on very systematically characterizing and fabricating superconducting devices. So, Anna, give her a warm applause.
Good morning, everyone. It's wonderful. Thank you to the organizers. This is my first time in Delft. I have to admit I'm a little bit jealous as compared to Chicago suburbs. This is such a beautiful place. All right, so today I'll tell you a lot about advancing coherence of superconducting quantum systems. This has been a wonderful journey the past 5 years of our new, but now not so new, National Quantum Center. This is the outline of my talk. I'll tell you a little bit about what SQMS does, what it is, this national center, what our goals are, what are our exciting partnerships, and then we'll dive a little deeper into what causes decoherence in chip-based superconducting quantum system, but also you'll see a lot of three-dimensional superconducting cavities, which really is our background, our strength, and the technology that we want to push at Fermilab to actually build a qubit-based quantum computer. Starting from the goals, first let me remind you a little bit what Fermilab is. We are one of the 17 national labs funded by the Department of Energy in the United States. We are historically the United States particle physics laboratory. We discovered different fundamental particles at Fermilab and co-discovered the Higgs boson with CERN. So really our mission is answering some of the most fundamental questions. Where do we come from? How does the matter, how does the universe work at the most fundamental level? Answering these questions has always required advancing instrumentation, advancing computing tools, advancing detectors, advancing accelerators. So a person like me, I came to Fermilab as a very young postdoc, and I have always try to push technologies to build very large particle accelerators, such as superconducting radio frequency cavities. And turns out that this technology then, later on, we actually turned not only for accelerators, but actually for quantum information science, for detectors, and so on. So quantum has become much and much more in the recent years for us at Fermilab, but generally in the Department of Energy complex, an interesting technology that we want to advance for computing, but also for sensing, for really advancing the tool set to fulfill our mission. So back in 2018, there was a National Quantum Initiative Act in the United States where there was substantial investments of the order of hundreds of millions of dollars for the Department of Energy, so actually $600 million to form 5 national quantum centers led by the national labs, but to really bring together national labs, industry, and academia under the same umbrella in mission-driven centers. So to really choose one major cross-cutting challenge in the field of quantum information science and then bring a collaboration together to attack this challenge. So SQMS, our center, stands again for Superconducting Quantum Materials and System. Our cross-cutting challenge that we chose is attacking decoherence of superconducting quantum systems. So we built it on our expertise and background. Again, my background has always been in understanding how to push the quality factors, so the coherence of these superconducting 3D resonators, and really link the nanostructure, so the fundamental properties at the nanoscale, with the performance of the device. So this was really the fundamental idea behind our center. And then of course, beyond that, actually what we do is we want to also advance this coherence, see it realized in actual systems, and also start to harvest the utilization of these quantum systems to advance some applications, for example, in particle physics or in condensed matter physics. So this is our collaboration. We are now over 36 partner institutions. The collaboration is led by Fermilab. We are funded at roughly $125 million over 5 years, and we are looking at another $125 million over the course of the next 5 years. So they're actually substantial investments. And you can see here, it's a really wonderful collaboration where we bridge, again, many universities, national labs, and industrial partners. We are actually over 300 researchers that have come together, again, from all these different backgrounds. And so what is our mission? So we want to bring transformational advances in the development and deployment of high coherent superconducting quantum systems. You can see here there is 4 main areas that I will be telling you about today. One is, that has been really at the core, has been abating qubit errors. So the fundamental science of materials and the nanostructure to advance superconducting qubit coherence. And so I'll try, of course, it will not be an exhaustive, comprehensive view of everything that we have done, but I'll try to give some highlights. The second area is building high coherent superconducting quantum system based on 3-dimensional cavities. So these superconducting cavities that, again, we use for particle accelerators, they can also be turned into quantum devices. If you couple them with a transmon qubit, you actually turn this whole object into a 3-dimensional qubit. And we actually want to build an architecture which is Qudit based. So we'll talk about that. Cryogenics is another area that is really our bread and butter. When we build particle accelerators, we cooled down kilometers and kilometers of structures down to Kelvin or sub-Kelvin. We also did support a lot of cosmic experiments in the milli-Kelvin, so there's a lot of expertise and facilities at Fermilab that now we are repurposing to advance cryogenic system for quantum information science. So I'll tell you a lot of the exciting partnerships that we have also with industry to actually enable more efficient cryogenics if you want to scale to very large quantum computing data centers. So if you start thinking going to thousands of dilution refrigerators, the conventional pulse tube technology starts to become not the most efficient route. And so we are working in that direction. Last but not least, why do we care? We have a lot of theorists and particle physicists and condensed matter physicists that want to utilize all of these wonderful new tools to really advance simulations for understanding the early universe. And so for that, our classical computers are not satisfactory. So we would really want to build a quantum computer at Fermilab to simulate things that we care about. And there's been a lot of quantum sensing experiments that we have done, for example, to look for dark matter or to search for gravitational waves. So if we will ever get to the end of this presentation, I'll give a glimpse to that. OK, so and then you will see a lot of this. Really, this is the core of what. So when you run a center this big, you do want to give it a major goal, and then there is a lot of other things that come with it. And so the major goal is advancing this superconducting cavity architecture to build the Cavity-qudit systems of record coherence for computing and sensing. And so here you see these 3D resonators that come in various shapes and sizes. And then we couple them, so you can see here, with a transmon qubit, which is on a chip that then you couple with the cavity, and they interact, and that's the whole 3D Cavity-qubit system. So we're building a processor with that. I'll show you some of our recent results, which are very exciting. In that process, of course, what we need to do is push the performance of the actual chip-based qubit, which can become, our cavities, we can make them with 2 seconds of coherence in the quantum regime. But the ancilla qubit can become the bottleneck. So that's kind of the motivation for us to push the coherence of transmon qubits. At the same time, we do this hand in hand with industry, for example, with our partners, Rigetti Computing. You'll hear from Andrew Bestick later in this week. But so we have been working in our interest to advance the 3D architecture, but also to help industry advance performance of chip-based processors. And we are looking at using these also as these cavities potential. As you build these qudit systems, you can also use them as memories and interconnects to scale, for example, even chip-based processors. And so that's also a direction. A lot of accomplishments in the last 5 years. We started, even building up these collaborations. And we have also deployed very large-scale facilities to be able to run all these experiments. And again, so some of these important milestones is what I will be telling you today about. So let's start with diving a little in the technical part, which is how do we understand, how did we approach understanding decoherence? And so these cavity tools, so what is the problem? Here is the cross-section of a transmon qubit. You have a substrate. There is sapphire or silicon. You have different layers of superconducting films like niobium. You have aluminum. You have interfaces between the substrate and the film. You have interfaces between the film and air. And you want to really understand what are all the loss channels. You want to understand two-level systems losses. You want to understand quasi-particles. Things that are due to magnetic fields, all the environmental effects. And so how did we approach this problem? Of course, you can study directly on the actual qubit. But one of the things that is complicated, as many of you who are experts know, is it's always a very convoluted problem. When you have to rely on models, and you don't know exactly how to isolate losses of the substrate versus the interface versus the metal. So one of the things that we did, capitalizing on these wonderful cavities that we have, is actually to utilize these cavities to really isolate things and try to understand study the subsystems one by one. So how do these cavities work? I mean, it's basically a big chunk of niobium, or you can make a big chunk of aluminum, right? So here, for simplicity, we show the niobium. So it's a 3 millimeter thick wall. On one side, you have just a native oxide. So you have metal, native oxide, 5 nanometers. And then you have the field, and then they are cooled on the other side. And so you're studying a very simple subsystem. So if I want to understand what niobium losses are and what are the losses in the oxide, I can study basically directly without having to infer how much that matters versus an interface versus the substrate. At Fermilab, we know how to make these cavities in the 10 to the 11 quality factor. So this means seconds and seconds of coherence, including in the quantum regime is what we have demonstrated. This comes from decades of investment in really extensive infrastructure to do surface electrochemistry, do high temperature treatment, clean room treatments. So it doesn't come for free. But it also comes with a lot of meticulous studies and knowledge of the actual nanostructure. So the first 100 nanometers are critical to determine the performance. And in fact, for quantum regime, the very first few nanometers, which is the oxide. And again, our approach has always been, we study something, we do even try empirically something, and then we match it with the material science, and you go hand in hand, and and then you iterate. And that's really what we have done with cavities and what we have done more recently with qubits. So we started to take these cavities in the quantum regime. Here, there's always a fun picture to show. This is a very large cavity like this that we use for accelerators, and then you can actually make them smaller and smaller. They start to resemble more quantum objects. So this is a variety of frequency from 600 megahertz down to, let's say, several tens of gigahertz. And you can study them in large-scale facilities like this, where you literally dunk them in 1,000 liters of liquid helium, or you can then put them into millikelvin fridges and start to really dial down to the real, true quantum regime at single photon level. And interestingly enough, I mean, for us, this was the beginning of the exercise to go from, thousands and billions of photons on the surface of the structure, all the way down to single photon. The physics of the surface changes substantially. And this is really where you start to see two-level system losses emerging. So 2 ways, right, that you use these cavities to understand losses. One is, again, just the surface itself. And the other thing is you can also put samples inside, like silicon or sapphire. And because the box is just a perfect box, which is lossless, then the losses are dominated really by the sample that you want to study. So if I want to study what silicon substrates dissipate, if I want to study what sapphire, so I can study that with parts per billion precision. So we used these tools to understand some of this. Here, some of the results, the early papers from Romanenko and Schuster back in 2017. This is what we call the quality factor as a function, as you dial down the power, going down to like low photon counts. And this that you see is the quality factor kind of decreasing. And so this is really the emergence of two-level system losses. And then we did studies where, so you can actually look at the native oxide versus if you, so with 5 nanometers where you anodize this oxide to, let's say, 100 nanometers. And so what we really saw is, you see a lot of curves here. So we changed, let's say, the level of interstitial impurities in the niobium, and you see that the two-level system losses are always the same. But if you actually, the only thing that really makes the difference is when you actually grow a thicker oxide. And so really this shows very clearly how the two-level system losses are localized in the surface oxides. And then we did a study where we compared very clearly a cavity that has, so down here the blue is a cavity. So by the way, these are photon lifetimes already quite respectable. Even with the native oxide, you have in the, let's say, milliseconds of coherence. But if I remove fully the oxide from the surface of the structures, you can actually go up all the way to seconds of coherence. And so by doing this comparison very systematically, where you look at a cavity with the oxide, you remove the oxide, you look again at the photon lifetimes. And by the way, this is with time of flight SIM, so you can see exactly what is happening. So with and without the oxide, you can see here. So you can actually extract exactly the loss tangent of the niobium oxide. And we've done this, for example, as a function of different frequencies. So this is just an example. So this study served several purposes. One is we showed that we can actually have cavities with record coherence of seconds, but also that we really understand where these two-level systems reside. And one of the things that we have done further is let's start looking at tweaking how we build this oxide, how we grow this oxide. And do I see always the same type of losses, or do I see that these losses are changing? And so that's also very important. When we look at these transmon qubits, we see a lot of variability. Where is this variability coming from? Does it depend on how I grow the oxide when I open the chamber, or when I inject, when I vent the chamber with something? And the answer is actually definitely yes. So here, for example, we did a study where first we asked ourselves, does it matter if the oxide is growing on a bulk niobium cavity or if it's growing on a film, right? So when we do transmon qubits, we deposit film. So in this experiment, we deposited film on a 3D structure, and we looked at the difference of bulk versus films. And the answer is we see exactly the same for bulk versus film. The only thing that really matters, again, is the oxide. So this was yet another confirmation that really all the losses in the quantum regime reside in the oxide. Another interesting study that helped us highlight. So yesterday during the panel, there was discussion. So someone asked, what should I focus on? If you ask me for the perfect surface, what does that mean? And the answer is, yeah, we don't know exactly, right? But so here, some of the light, so we shed some light, for example, with this experiment where, so how do we get rid of the oxide here? We bake, essentially, the cavity, and we cook it literally at 300, 400 Celsius in ultra-high vacuum. And you keep the surface, the cavity under vacuum. So the oxide dissolves in the niobium. You keep it under vacuum, it doesn't regrow. So those are the studies that I showed you, where you compared with and without. You can also do partial dissolution, where you actually start to bake it sequentially at lower temperatures and see what happens. And so part of what we have seen here is, let's say, so I bake it for 200 C for 1 hour, then another 5 hours, then another 5 hours. And what do I see in terms of the total TLS losses? I actually see a non-monotonic behavior. So remember, what I showed you earlier is that I can get it to be very low if I bake it fully, if I dissolve it fully. But what happens in between is that first you see the T-level system losses get worse until they get better. So why is it so? Part of this we answered by doing different materials analysis. And what we found, for example, by doing XPS and by looking at the amount of vacancies in this surface, in these oxides, what we actually noticed is that there is an interplay, essentially, of the so as you start to bake these cavities, so you start to deplete the oxide of oxygen. So it becomes more defective. So the number of vacancies goes up. But then, at the same time, what is happening is that your oxide is thinning down. And so that's where the interplay is coming from. So you're making the oxide more defective, and at the same time, you're making it thinner. So, so that gave us some sense that really, you are looking really at disorder, at vacancies inside these oxides. We have also done several studies more recently, and we have not published this, but I just wanted to say that these curves are showing you cavities that we have, this is no oxide, then we expose it to air, then we do again the same treatment where we remove the oxide, and it's good again. And then we have done things where we have regrown now this oxide rather than in air under different conditions, which again, today I will not say exactly how. But the takeaway here is actually that we were able to improve the losses by over a factor of 3. So you can grow a much better oxide under different conditions, let's say better heat conditions and better impurity conditions. So proof of principle that, and this is important for us also because when we want to build this quantum computing system based on the 3D cavities, part of what we want to do is we want to preserve this very high coherence of the 3D cavity. But when you need to insert the ancilla element, you have to vent them. You have to open them up to air. And so we don't want to lose their advantage. And so this actually for us, it's also important for that. We have done a lot of studies also, as I mentioned, to understand, for example, losses in sapphire or in silicon when you insert these samples inside these cavities. So here you see some nice pictures, so you can put a silicon rod or again a sapphire rod of various different resistivity. We work with the various vendors like Kyocera and others to really understand, for example, their processes that they do on sapphire, how it changes in terms of the loss tangents of the substrate. And so here there are some results in terms of silicon, in terms of the also, yeah, this is actually silicon. I think for silicon we saw loss tangents. We have never personally seen like loss tangents better than in the maybe mid 10 to the minus 7 or so. So sapphire for us has always been the best. And then, we have done also some studies to really understand, and so decoupling effects of oxide versus bulk in terms of where these losses are residing. And then here in this, you actually look at the sapphire. So I think what's interesting here is we compare the same exact sample. So you can see that as received here, you have a sapphire sample that has like maybe 3 × 10⁻⁷. And then you can actually anneal it, and you can see a substantial difference where you go down an order of magnitude. So we look at all these different treatments and so on to really understand. And so part of again, doing the material science is seeing what is changed, why my sapphire substrate has 1 order of magnitude difference in terms of losses. And so one of the answers is that with the annealing, we have definitely created an atomically flat surface, but also we have decreased the paramagnetic impurity concentration in the bulk of the materials. So again, some hints of what may be driving and giving us less TLS loss in this. So if you put all these things together, again, we have done numerous studies that I will not be able to all show here, but we have looked at aluminum cavities, right? We have looked at a lot of things, and then you can put it all together and start to build a hierarchy of losses. So what matters the most? Is it the bulk? Is it the interface? So when you start to look, and then you can also kind of do a back of the envelope with simulation and put a cap and say, okay, if my silicon has a loss tangent of 10⁻⁷, that caps my transmon qubit lifetime for a particular geometry, let's say 300 microseconds. So definitely we need to do better there. Sapphire, with the best that we have seen, it caps you at roughly a millisecond. But definitely I would say the most dramatic is the surface oxide. So if you have niobium oxide is quite bad. And so that's why we were so focused at trying to make it better. Tantalum has a much better surface oxide. And so part of what we have done is actually, once you build an hierarchy, is let's now attack the problem one by one. And so that takes me to the next part, which is fabrication. So again, this is kind of how we work in the center. We have an area where we actually do actual preparation, fabrication of devices, then we do characterization, then we do structure, chemical, and microwave loss and characterization of materials, as I just described. We have a group that does simulation, theory, and modeling of losses, and then this whole thing works in a nice virtuous cycle. We call actually these groups as nanofabrication task force. We have this round robin, which really is the people that are measuring the qubits in different locations across the center. Performance variations group, a cavity-based loss characterization, which I described, and a loss budget, more theoretical group. So for the nanofabrication task force, actually, across the center, we fabricate qubits across several foundries. So we have people at Rigetti Computing, our partners, at NIST, and Northwestern, and our group at Fermilab actually goes to University of Chicago Pritzker Nanofab. And so the idea is really we all have a standardized geometry. We're all working with the exact same geometry. So there's no misinterpreting there. And then we change things one at a time. Are we all seeing the same results when we change, let's say, one parameter, if we change the substrate or if we change the surface encapsulation? And then really do the cross-check across different foundries. So these are some of the directions that we looked into. We have changed and done an optimization of the base metal layer. We have looked at different geometries. We have done optimization of the JJ footprint, improved fab processes with substrate preparation, etching, and so on, qubit package, and then, of course, the substrate, as I mentioned. So again, there are so many variables, right? But we have been trying to really change, again, things one at a time to really understand what matters the most. So here we looked for the metal base layer. And again, I will be going fast, but feel free to catch me after to have more details of what interests you. We have looked at niobium, tantalum, and rhenium, for example. And I would say the best results we have gotten you can see we have gotten reasonable results also with tantalum, half a millisecond, even with rhenium. With niobium, actually, in fact, I'll show more recently, we have also exceeded a millisecond. But again, with niobium, you will never get there unless you replace the surface native oxide. So the best results with niobium are when we actually encapsulate it with the different oxide layer. And so that takes me to this slide. So in this study, what we did is, so we have same base metal layer, niobium. And then in one case here, we have, let's say, native oxide. In this case, before we vent the chamber, we actually deposit tantalum, about 10 nanometers or so. In this case, we deposit aluminum, tinitride, gold, for example. So keep base metal the same and then change the very top, and this gives you really a clear comparison of what surface oxide in principle dissipates dissipates the least. And so what we saw is the actual tantalum and gold were actually the best, and the results have shown that, in fact, we had roughly, and of course, this depends, and so we studied also as a function of geometry, right, so that you can really understand it in detail. The best results are for the large paddle geometry. We saw up to 600 microseconds of coherence and that we did this also at Rigetti, in fact, where they compared. So we did it on sapphire, Rigetti did this on silicon, and so they also saw a really nice improvement, I believe a factor of 2, going from non-encapsulated versus encapsulated. So definitely, clear that when you use tantalum oxide, it's way less lossy than the niobium oxide. And in fact, you can extract the two-level system losses. The loss tangent of the tantalum encapsulated qubits have 8 times less TLS loss and compared to the actual niobium. So this, and I think this is actually in line with other values that we have seen in literature. So we have done also some statistics, not a huge amount. It takes a lot of time, but if you look just at the Fermilab data over time, you can see clearly a nice trend. But then we have taken, so we now can really see, at the beginning when we started to make qubits 5 years ago, they were in the tens. Now we can really, I think we hardly see qubits less than 200 microseconds, and we start to see a lot of qubits actually in the hundreds. Even in excess of a millisecond. So things have gotten definitely better. We have tried to really look at, as I said, change one thing at a time. So how much better are things when I change, again, the substrate, or when I change the deposition of the base metal, the temperature deposition of the base metal. So there, for example, we saw that when you deposit niobium at 800 Celsius, it's always better than when you don't deposit niobium with an unleavened temperature versus room temperature. We have, for example, played with the Josephson junction footprint. Doesn't matter, because based on the simulation, actually, that should also matter at a certain point. Once you start to abate all the surface oxide losses, then the JJ area will start to matter too. We have looked at package, chip layout. Many of you are probably familiar, but of course you have to be very careful. We have seen things that if you're not careful, the qubits on the edges are more dissipative than the qubits in the middle, and so there we have modified our geometries to make sure there is no extrinsic losses like that. We have done all of this. We have been able to see basically chips with really good values on average, even systematically across. But we have also asked ourselves, can we go systematically beyond a millisecond? In the next few years, we have put for ourselves a very ambitious goal of actually reaching 10 milliseconds. Is that possible? We think it is possible. We're just working one by one. Here is our 3D qubit chip layout. So when you want to couple it with the superconducting 3D cavity, it's still a transmon qubit. It's just more elongated like this. And so one of the more recent results is actually that for these type of qubits, we actually saw even 1.2 milliseconds of coherence. Again, we combined a lot of these lessons learned, niobium at elevated temperatures, encapsulated with tantalum, reduced JJ footprint, so everything that we learned. And then it's also the perfect box, right? So if you put the qubit inside a 10 to the 11 cavity, you definitely don't have box losses. So it's possible, and we'll be marching towards even better numbers. But let me also say that things are not always, of course, you do one chip and you don't always get 500 microseconds. We still get some variability on the same chip, qubit to qubit. And so a large study that was done that we actually recently put on archive is why I have performance variation, qubit to qubit, and can we identify correlation and trends between material and superconducting properties and T1 times. So I'm very proud that SQMS has this amazing collaboration where we have basically thrown the kitchen sink of material characterization from the more conventional microscopy to exotic things like muon spin rotation or terahertz spectroscopy, but in a really coordinated way where we really take things that are characterized and compare good versus a bad qubit and what can I see that is there to understand the differences. And so here are just some highlights of things that, and you can only imagine how time-consuming these studies are. So we have looked at dozens of fragments across many institutions. But so things that we asked ourselves is, when I look and there is like a trench depth, is there a relationship between the trench depth and the performance? And the answer is yes. Is there a correlation between the niobium oxide thickness and performance? So you can see indeed that the oxide varies, from qubit to qubit, and so is there a relationship? Actually, we do see potentially a correlation there. The sidewall may matter. I mean, sometimes you see a sidewall like this, sometimes it's like this, sometimes it's like this. There is an undercut. All these things combined with simulation, actually, it can give you substantial differences in terms of the field distributions and therefore in terms of the ultimate performance. So those are things that are important to know and then important to attempt to control or to use at your advantage. We have combined all of this also with the various theoretical studies. We have this group at Northwestern of James Rondinelli that has looked at more computational models, and his conclusion is that oxide layers, why tantalum oxide is better than niobium oxide, they exhibit more robust stoichiometry compared to oxide layer niobium, and for a given degree of oxygen deficiency, the magnetic moment formation is suppressed in tantalum oxide as compared to niobium oxide. So that could be a potential interpretation of what's happening there. This seems to be also in line with the results that we have from, this is a study that we did at PSI here in Europe, in Switzerland, where you actually implant muons on the surface of samples. And then you look at the spin precession of the muons in the magnetic field, and you can understand, if there is field, or you can do it in zero field, you can understand if there is magnetic moments, how many, as comparing, for example, niobium oxide samples versus tantalum oxide samples. There's a lot of things that you can learn from USR, but we definitely saw that there are things that are better in the tantalum oxide compared to the niobium oxide in terms of magnetic impurities. Another thing that actually worth mentioning here, a lot of studies that we have done is also looking at niobium hydrides. So that's something that we had studied extensively in cavity world. So niobium is a sponge for hydrogen. So when you actually cool down niobium with hydrogen, you can have precipitation of this niobium hydride compound, which is non-superconducting. So you can see here, so we looked with the, for example, cryogenic microscopy, so with the SEM at cryogenic temperature. And you can see these objects really precipitating and forming. And so you can ask yourself, what do they do? Do they damage performance? And for example, one thing that we know is, as you warm them up, they disappear. You cool down, they're there, but they change in size. They can move around. And so those could also be responsible, for example, for performance variation. So we have looked at niobium hydrides. And we have also had Jim Sauls looking at also theoretically understanding the role of hydrogen, for example, in deuterium in niobium, and how this could also be a potential model for two-level system losses in the actual metal. Okay, so let me just show a little more of, so this is all very nice at the material science level, fabrication level. We also look at I'm a strong believer of studying at the device level. So you look at performance and you do some level of diagnostics and you try to understand at device level what's happening. So one thing we have done is we asked ourselves what is the role of magnetic field. So when you cool down your qubits in some level of magnetic field, how much is sustainable? For cavities, not a lot. If you want to really keep this high bar of seconds of coherence, you have to actually watch even 10 milligauss. So you have to screen really, really well. And so some of the studies we have done are by putting cavities in Helmholtz coil and cooling them down in dilution fridges under different field configurations. And so it's possible to maintain seconds of coherence. Again, you have to be very meticulous how you shield everything. But then we did the same studies with this 3-direction Helmholtz coil for qubits. And so we applied magnetic field in various directions. So we cooled down transmon qubits in various level of magnetic fields up to, for example, here you can see 600, 800 milligauss, 1,000 milligauss. And we asked ourselves, up to what field can I maintain high coherence? And so what we saw is actually, to my, I was very pleased to see that, because in the cavity world, as I said, I had to worry about 5 milligauss in my career. Here, you can actually cool down these objects in hundreds of milligauss, and you can still maintain very high coherence even in the hundreds. You can see here we have 300 milligauss, 300 microseconds even in 600 milligauss, which is very promising. But then, interestingly enough, we can see that there is some sort of threshold effect. As you apply above a certain field, you actually kill completely coherence. And we're trying to understand that. Most likely, this is flux that starts to creep in the junction area. I think one thing that I want to draw attention to that was very interesting of this study that was new, very new, was that we noticed that in both cases, if you trap magnetic field when you cool down, or we have done also that you cool it down in zero field, and then you turn on the magnetic field during operation. So in both cases, what we notice is that the spread in T1, so how much T1 fluctuates, actually decreases substantially when you turn the magnetic field on. The larger magnetic field you apply, the more the spread decreases. So that's interesting. It gives you some hint of what maybe we are saturating some magnetic moments and so on. So that's interesting, something worth exploring. Okay, I have only 5 minutes, and I had so much more, but I just want to say that we are doing studies also looking at the effect of cosmic rays, and we compared performance of qubits above ground at Fermilab and underground at Gran Sasso in Italy under kilometers and kilometers of rock. This is something that worries Google and others very much. So we have looked at the effect of radiation by exchanging and in fully shielded configuration versus not. So I'm going to skip through, but I can tell you that we have seen that actually our qubits are quite robust. Maybe we have, as compared to what you expect from simulation, what we see, we have about maybe 10%. We pick up 10%. We also have put a radiation source, so we pick up about 10% of events. So that's reasonable. And we have also looked at doing these studies for different materials. So when you change the base layer, the substrate, what kind of difference you see. And there is publication that's coming up on this that it kind of informs what is the best materials configuration to be more resilient to this type of effects. Okay, I'm going to skip here, and I just want to tell you in the last few minutes what is more important for us, which is the Cavity-qudit systems. So we are building a quantum computer at Fermilab that is based on these cavities. This is a zoo of cavities here that exist in literature. We know that the group of Serge Rosenblum had some beautiful results recently on utilizing these mushroom cavities with the very high coherence times in the tenths of milliseconds. So because you have this very high coherence, you can actually leverage the very high coherence to do qudit encodings, right? So I guess I should just show you the results. So here's an example of our recent results where we're able to build up to 20 Fock states, and you can see that the coherence is still 1 millisecond for Fock state 20. So and again, this is without taking advantage yet. This is for a cavity that is still with the oxide and everything. We can do so much better, and that's what's coming next. So we have done, this paper went on archive, I believe, a couple of weeks, maybe like a month ago. So I invite you to go and look at it. But again, we have these beautiful results. We have, I think, so for a multi-qudit system, this is a record. It's about, I believe, over 20 millisecond lifetime. And maybe let me just say that with actually 3 nines of fidelity for our first gates. So we're very excited about these first results, and these are the foundational results for what we're going to build, which is, and so maybe I'll just stop here since I'm out of time, but so let me just say that for the next few years, our goal is to build a 100-qubit quantum computer at Fermilab based on this technology. It will require, can I show just one last slide? Maybe let me just say this. Yes, so, okay, and the visuals are very poor. So those are the 3 goals for our next 5 years. Still pushing qubit coherence breakthroughs for both working with Rigetti, but also for ourselves, the 100-qubit computer, and then the unit of a quantum data center prototype where we will be connecting 2 fridges with the chips or cavity-based systems on both sides and utilizing our cavities as interconnect. So we're very excited about the future. And again, thank you very much for the invitation.
Great. We have already some question. I see David was very fast getting his hand up as an experienced person.
Thank you for the amazing range of things that you're doing with your quantum materials and all other things. I have a question about the very last thing. There's this great experiment at ETH where they've connected 2 fridges over a 30-meter connector. That wasn't exactly what I saw there, but have you been thinking about experiments that somewhat mimic that and look now into the sort of quantum communications aspects of connecting?
Thank you for the question. Yeah, exactly. So the WRF experiment is really exciting. Yeah, and I don't know why I'm sorry for the resolution being so poor. This is a little bit like that. So this is meant to be a microwave interconnect. But the concept here is actually to utilize our cavities. So there are some papers back in 2017, I believe, from the Vienna group and also from some Chinese group that show that if you have these cavities, you can actually, we want to show that this can be a 4K link. While the WRF is a milli-K link, we're going to do it at 4 Kelvin. So, and so this is really to do some proof of principle of, when we scale to large data centers, and it's less convenient to do, very large, very long lines and millikelvin. This 4 Kelvin will be much more simple. And so yeah.
Concept papers on that work?
There are concept papers, and so we would be the good place where to realize this because of our cavities. And if you think about these qubit systems, in fact, this can also very much help with that. So we can talk offline, but that's one of the ideas. And so we will be working actually with IBM to connect 2 IBM small chips, left and right. And then so the IBM chip talks to our cavity, talks back to another cavity, and then goes back to an IBM chip. And this will be used also to scale in the future our own cavity-based systems.
Okay, great, thanks.
We have a question here.
Hello. Yeah, thank you for the very nice talk. I had a question about encapsulation.
Yes.
So why does niobium encapsulated with tantalum perform better than tantalum itself, when in the end it's only tantalum oxide, which is on the top? And in fact, like the side walls of niobium are not encapsulated, and niobium oxides are a bit lossy. Yeah,
I mean, it's the very reason why we did that experiment, in a sense, which is we know, right? What did I show you today? I showed you that niobium cavities, if you don't have the oxide, can have seconds of coherence. That means that the niobium metal loss is negligible. So it's below 10 to the minus 10, right? So you can, in our world, we call it 1 or 2 nanohm of surface resistance. But what do we know of the surface resistance of tantalum? So what is the metal loss in tantalum? That's something that I actually don't think it's very well studied. And so the answer to your question is, my impression is that tantalum definitely has a better oxide than the native niobium oxide, but the metal loss perhaps is the other way around. Perhaps niobium has a better base metal as compared to the losses in tantalum. So we want to study this better. We want to make some tantalum cavities and so on. So anyway, we'll get that more clear.
Yeah. Thank you.
Good. Final question. So many to pick from. Let's go geometrically somewhere else in the room.
Thank you for your talk. Just a bit of a general question. Do you plan to explore nitride-based superconductors or possibly nitridation of substrates?
Of substrates?
Yeah, like substrate surfaces.
Do you mean like the metal, or do you mean this? Oh, so you're saying instead of working with niobium, working with nitrides?
Yeah, that also.
Yeah. We looked at maybe a tinitride or something, but typically I think nitrides, it's a little harder to hit the perfect phase, right? You will get the good phase and then you'll get some spurious phases, at least in my experience. I work with niobium nitride, and that was the issue. You can get the good phase of 18 Kelvin, and then you get a lot of mixed stuff of 1 Kelvin. And so I'm typically not a huge fan of that, but sure, one can. I think rhenium is one thing that looks promising. It's difficult to work with, but it seems to be really lossless in terms of surface loss.
Thank you.
Great. Let's thank Anna again.
Thank you.
Our Delft Blue present for you. A small comment to the people in the back. Just don't hesitate to walk past people. We still have a lot of seats in the middle, so just go in, take a seat. It's okay to walk past people. And to present the next session, we have Alessandro Bruno from Quantware.
Thank you very much. Good morning, everyone. Let's get started with the first round of speakers for the scientific session. The session is about materials, fabrication, and devices. So I hope that we will have a very interesting conversation. So the first speaker of the morning is Jonas Govenius, recently founded Arctic Instruments, and he will talk about native oxide passivated tri-layer junctions for superconducting qubits.
All right, thank you, Alessandro. The microphone is working, I suppose. Thanks for the invitation, and good morning to everyone. I'm Jonas Govenius. This work on these native oxide passivated tri-layer junctions was carried out at VTT, where I used to lead a research team. So, of course, a huge thanks to my former team members. I'm no longer at VTT. Now I'm at Arctic Instruments full-time. But we have a stand here, so if you have any questions, you can usually find me there after the talk. We also got some theory support from Jukka Väyrynen at Purdue, so I want to acknowledge that as well. So, okay, I thought I'd say something about why you would want to look at alternative approaches to making junctions, but maybe you can just believe me that you'll need a lot of junctions in the future if you want to achieve any of these applications. And the yields we can reach with Manhattan or Dolan bridge type junctions, I think you'll have a hard time pushing beyond like 3 or maybe 4 nines in the yield. So that's going to be a challenge in the long term once we fix the coherence time issues or gate fidelity issues. So what other approaches do we have? Well, I made this kind of a 2D map here, and I expect you to give me a hard time about this because it has poorly defined axes. So on the y-axis, we have essentially coherence time, and on the x-axis, we have something even less well-defined, which is scalability. So at this corner, we have the Manhattan qubits, which of course achieve the record coherence times. On the other hand, they use fab approaches like angle evaporation and liftoff, which sort of lead to this maybe 3 or 4 nines of yield. In this opposite corner here, we have these tri-layer based junctions. like MIT's 8-layer SFQ process. So those can produce very large junction counts with very high yield. But on the other hand, they use things like amorphous dielectric layers, which essentially kill your T1 times if you would try to make a qubit with this process directly. In the middle, we have various other approaches, like there are the overlap junctions with or without liftoff. Then we have various released structures that I think are a bit similar to MEMS devices in some ways. And by the way, we have a talk about this right after mine, I think. And I didn't quite know where to place it, so I put these arrows here, so forgive me about that. But one thing I want to highlight is this so-called swaps junctions, which are they belong in this category, but the work I'm going to present is derived from this swap junction. So then, yeah, what are these swaps junctions? So it stands for sidewall spacer passivated junction. They have all these great properties in terms of processability and achieving great yield, but they have one major issue for qubit applications, which is that they include the spacer oxide here, which is very lossy. So I think, as such, you wouldn't expect to make a good qubit with these junctions. So the spacer oxide is circled in red here, and its purpose is to isolate this niobium here, which is the top electrode, from this niobium here, which is the bottom electrode. And here you have the tunnel barrier in between in this tri-layer. So what can you do to avoid the spacer? Well, you could, of course, remove it. And that's what was done in the Schuster group in Chicago. And that's possible. And they demonstrated promising T1 times up to tens of microseconds. But as they mention in the manuscript, this etchant they use actually dissolves aluminum as well. So I think it's not the approach you should pick if you want to ultimately reach very high yield. And indeed, we tried over the years various approaches to removing the spacer, and we always found that we either etch aluminum or we form these very hard to remove fluoride compounds on the surfaces of niobium. So we decided to take a different path, and we developed these so-called native oxide passivated or NAPA junctions. And the structure looks like this. So it looks kind of like a swaps junction, but you have this additional via here on top. Here's the cross-section. And the point is that here, so we swapped the bottom electrode material from niobium to aluminum. And then we just use the native oxide that forms on the side of the aluminum here to isolate it from the wiring layer, the niobium wiring layer here. And we think this should work because it's essentially the same oxide that's used in the tunnel barrier anyway. So if it's good enough for the tunnel barrier, it should be possible to form it with high enough quality on the sidewall as well. And it has smaller participation ratio in the sidewall than in the tunnel barrier. So in principle, it should be OK. And the fab steps are very conservative. It doesn't lead to any suspended structures in the end. So in the end, I think this is quite promising in terms of scalability. It does require this additional via that I'll explain shortly. But really, it's only more of the same in terms of processing steps. So, OK, I'll be very brief on the fab. You start from tri-layer deposition, so you form the tunnel barrier in the very first step on a pristine wafer, so that's very nice. Then you etch the bottom electrode, and then you let the native oxides form, and this oxide here becomes the passivation oxide. And now you deposit the first niobium layer, and crucially, you do it without removing the oxides before this deposition. So that ensures that you don't damage this sidewall passivation here when you grow the oxide. It has the unfortunate side effect that you also don't get electrical contact to your junction here, so that's why we need to add this via. And that's explained here, but basically you etch this hole on top, and then the oxides form, but then before you deposit a second layer of niobium, this time you do an in situ oxide removal but it's okay because everything is now covered by this niobium 2A. So you don't damage anything other than the niobium 2A surface, which is covered by another layer of niobium right after that. And then you etch that niobium, and ultimately you end up with this structure. So what do you have here? So the red color that's the aluminum bottom electrode, and these blue layers are the niobium top electrodes. You see the via, this hole here, and in this cross section, this is like the via area, so it covers almost the entire junction. There's the tunnel barrier, the bottom electrode, and the current path goes from here up to the top and through the tunnel barrier. So we can look at this in more detail under TEM and EDS. And yeah, so it basically confirms that, okay, first of all, we do have the oxide visible in this oxide map here. That's the passivation oxide. And then we have some other oxides that are kind of parasitic, but they are fully surrounded by niobium, so we think it's okay. Then also we don't have the oxide here in the via region, so indeed there's a continuous path here from the tunnel barrier through the niobium to the top electrode lead here, going off to the side. So basically, it looks like it should work, and indeed, when we measure the room temperature tunneling resistances, we do see a conductance that scales with the area and not with the perimeter of the junction. So that says that the tunnel barrier dominates the conductance. It's not sidewall leakage that dominates. We see it over an order of magnitude in linear dimensions, so 2 orders of magnitude in area. Yes, and then indeed, when we cool this down and measure an IV of just a single junction here at 40 millikelvin, nominal size around 600 nanometers, we see a typical SIS type IV curve. So we see a gap voltage here matching the sum of niobium and aluminum gaps, and we see a critical current branch with a reasonable order of magnitude for the switching current. There's some excess conductance if you zoom into this region here, but in the interest of time, I think I'll skip it and just say that it's typical for niobium junctions. Then going to actual qubits, so I'll just briefly mention that basically the capacitor geometry is like an X-mon geometry here with a 20 micron gap, and but unusually we use 2 junctions in series in order to essentially allow us to make almost a full capacitor structure out of just 1 layer instead of a mixture of aluminum and niobium. So this way we can limit the volume of aluminum to a very small island between the 2 junctions. It has some complications. It has actually great charge sensitivity, even though you wouldn't expect it, but it has a relatively low anharmonicity of 56 megahertz here. But we still think it's, for this kind of material study purposes, it's a kind of a transmon-like enough to make sense. So indeed, then when we do the qubit measurements, so here's the best qubit, we see all the sort of signatures of a transmon qubit. We see the 1 and 2 photon transitions. We can extract the anharmonicity matching the simulation. We see Rabi and Ramsey, and here are the time traces of coherence times. We see at best something like 36 microseconds, but maybe the time average is more like 30, which is, but I highlight that the qubit frequency is 5.2 gigahertz, so it's not a super low frequency qubit. So actually the Q factor of this is 1 million, which I think is, it's of course behind the Manhattan qubits, but I think it's the best tri-layer type qubit result out there, in fact. Then we also studied some other variants, like we studied the impact of making the shunt capacitor either out of the niobium layer or the aluminum layer, which is just like a layout difference. So ultimately the junctions are identical in both cases. Yeah, I think here the conclusion is ultimately that you can't can't sort of say whether where the results exactly come, where the limitation exactly comes from, but you can say that for the best kind of process variant, we were able to quite consistently achieve these Q factors in the high hundreds of thousands, or just below 1 million. So I think my time is basically up. Just wanted to conclude by saying that I hope I gave a glimpse of why I think it makes sense to also try to push for this corner of the graph from the direction of the very high yield but low coherence junction strategies, and not only from the very high coherence but low yield direction. I think both approaches should be pursued, but I think this hasn't been done that much, I think. And yeah, okay, that's just a repetition of what I just said. So we did this proof of principle Napa junction based qubits. And I think this, what I didn't emphasize was that I think this has really good potential for leveraging modern tools, modern fab tools. Finally, I want to just take a minute to acknowledge the contributions of Leif Grönberg. So probably any device coming from Finland in the last 40 years involving niobium has had Leif's hands involved in the clean room, and he's retiring this Friday. So I wanted to acknowledge this here. Yeah.
Thank you very much. Time for question. First hand was there.
Thank you. Thank you for the talk. I think that maybe you mentioned it, but I missed it. But why do you use the double junction versus just using a single junction, like tri-layer junction?
Yeah, it had to do with the motivation of being able to study where the dominant losses come from. We didn't quite get there, but we thought this could be a good idea so that in this geometry, you can have both the ground plane and the central electrode of the XMON made out of the same layer, like in this case, the niobium layer, without any parasitic junctions. Because otherwise, if you have just one junction, well, then you have different materials for the two leads, and you have to somehow go from aluminum to niobium. And you can do it, of course, by putting a very large parasitic junction in series. That's kind of the typical method. But then there are the questions about what's the impact of that large parasitic junction. So we thought that this is kind of a bit more, like this more well-controlled sort of a situation for that. Yeah.
Thank you.
Next question. I think we have another. Oh.
Yeah, thank you for the very nice talk. I was wondering, before you went to the native oxide passivated junctions, you worked for a few years on the etch process, and you saw you would either etch aluminum or leave fluoride compounds on the niobium.
Yeah.
And I was wondering, are these fluoride compounds actually a problem? Do you have like measurements where they showed, oh, okay, this is actually really bad for the coherence?
So we never made qubits, but it looks terrible. Like if you sort of, so yeah, in extreme cases you see them in optical microscopy. In less extreme cases you have to go to maybe SEM or AFM, and then you start seeing them. And they just looked, you know, like sort of tens of nanometers or even sometimes 100 nanometer like particles on your niobium film. So it just seemed like it was not a good idea to proceed.
Yeah, clear. Thank you.
We are just out of time, so thank you again. Actually, a small present.
Thank you.
Next speaker on stage is actually Matvey Finkel from TU Delft, and he will talk about self-aligning hard stop for a flip chip architecture.
Thank you. Thank you for the introduction. Hello, everyone. My name is Matvey Finkel, and I'm going to talk about self-aligning hard stops for the flip chip architecture. So the modular flip chip approach is currently one of the main approaches for building large quantum processors. And the idea is that you have a single bottom chip with all the circuitry, and then you can put the top chips with the qubits which are capacitively coupled to the circuitry on the bottom chip. And then you can actually build larger quantum computer. And the key advantage is that it is much easier to fabricate multiple medium-sized chiplets and build out of them a bigger quantum processor than just a single monolithic chip with many qubits. So since it's only the capacitive coupling, it is very tempting to, in principle, it doesn't require the DC connection between the chips, between the bottom chip and the top chip, because the qubits can just basically capacitively couple to the circuitry. And that gave the idea of having these self-aligning hard stops. So basically, we have the hard stops present on both chips, matching each other, so that the smaller hard stop on the top chip goes into the opening in the bottom chip, and that kind of gives you the precision, the accuracy in positioning the two chips together with the vertical accuracy based on the thickness of the hard stop, and also the lateral, because they kind of get this lock-in action. And then the vision is that we can actually have a bottom chip with these donut-shaped hard stops, and then we fabricate a top chip with qubits, and then we can do some preliminary testing. Oh, okay, I'm doing something. Yes. Right, I get a little bit of animation here. But basically, the idea is that we can cryogenically test it and then safely remove it and store, for later use until we want to actually build a larger quantum processor. And they are fully reusable because there is no indium bumps. It's just a mechanical, fixing of the chiplets together. So that's a very nice picture, but it comes with the strong requirements for the hard stops. So first and foremost, they have to be mechanically and chemically stable. So ideally, they have to survive all the fabrication hardships of the bottom chip and the top chip, and also survive multiple cool-down, warm-up cycles, so that you can fully leverage this idea of pre-testing and then building the processor. And then, of course, they have to have the reproducible height so that we can have the reliable distance between the chips and predictable capacitive coupling. And they also need to have the accurate in-plane dimensions so that we can also have this, predictable overlap between the elements of the top and bottom chip. And then, of course, the important requirement that they have to be not damaging to the quantum surface plane. So they have to keep the superconducting base layer pristine, so high quality factors. So we use the amorphous silicon as a material for the hard stops. And with the special adhesion layer, it actually gets a very excellent mechanical strength. So we can sonicate it in nitric acid and HF, and then we do multiple cooldowns without any visible damage or decrease in the function. And then the height is determined by the growth rate of the amorphous silicon, and we routinely get about 1 micron reproducibility, and the uniformity across a 4-inch wafer also about 1 micron. And then we use a dry edge to actually, for the final definition of the hard stops. And in principle, we can get a micrometer accuracy there. But for our initial tests, we decided to go for a bigger margin. So we have 250 micron opening in the bottom chip. And then this 200 micron insert goes into on the top chip goes into that opening. And then not damaging the quantum plane, we achieve by limiting the exposure of the quantum plane to the adhesion layer and the amorphous silicon only to the places where the hard stops are. So everywhere else, it's a pristine surface. To further prove that point, we fabricated a simple test resonator chip with fully functional hard stops, these 3 donuts here. And then it has a single feed line and 15 CPW resonators attached to it, coupled to it. And we have 13 resonators with our standard dimensions of 12 micrometer width, center width, and 4 micrometer gap width. And we also added 2 wider resonators to the sides with a twice bigger dimensions, just to check if we can see the participation ratio effect. And we get a nice resonant dips and a resonant circle in the IQ plane, which we fit with the equation to extract the key parameters of the resonators, the coupling quality factor and the intrinsic quality factor. And this last one, intrinsic quality factor, is actually what we cannot really control. We just, that's what we try to optimize with all this work. So we measured this chip in the dilution fridge. And of course, we do the normal power sweep to achieve the single photon regime for the resonator, for each of the resonators. And I'm very happy to tell you that they are all above 1 million. And then for the, for the standard smaller dimensions, they average around 1.3 million QI in the quantum regime. And then for these 2 wider resonators, we get 2.2 million. So that's very promising. And to further, check the feasibility of this approach, we also fabricated a simple qubit device to actually check out these 4, requirements or feasibility proofs. So, well, first of all, we wanted to check that the qubits are actually feasible and they have some meaningful coherence. Then we wanted to check the uniformity of the inter-chip coupling strength, and then validate the chip reusability. And lastly, but not least, we wanted to prove that thermalization is still effective, even in this, without indium bumps, just mechanical coupling. So for that, we designed a simple chip. So again, fully functional hard stops, and we have a single feed line and 10 readout resonators in range of 7 to 7.9 gigahertz attached to it. And then for the qubit chip, we have 10 fixed frequency transmons, which are coupled to the resonators later on. And the only metal here is this color, this orange color, so they're really floating on the chip surface. And then the assembly goes like this. We have a fully wire bonded bottom chip, and then we put the top chip, which is smaller, so that the bottom chip is around 10 millimeters size, and this one is 7. And then we align the hard stops so that they actually get locked in. So here you can see this dashed circle. That's a hard stop on the top chip. And then you can see how it nicely fits into the opening on the bottom chip. And then the qubits are coupled to the readout resonators by just being on top of them. And then we fix everything with a fixing spring and put it in the fridge. And then for the measurements, we do the standard measurement. So we first find all the resonators on the feed line spectroscopy. And you can already see that there is something going on with the middle ones, but I will come back later to that. And then we do the two-tone spectroscopy to find the qubit frequency. And then we analyze the coherence and the qubit unharmonicity. And yeah, the target the charging energy is pretty much what we aimed for, so that's good. And also the frequencies are close to what we aimed for. Right, so we tested two different top chips on the same bottom chip, and they give the pretty much similar results for the qubit coherences, around 10 microsecond. And again, the 3 qubits in the middle are missing. And again, I will come back to that later. And then for the inter-chip coupling strength, we use the lamp shift of the readout resonators to determine the qubit resonator coupling rate. And they all nicely line up at around 200 megahertz for both different cooldowns, different top chips on the same bottom chip. And now the mystery of the 3 missing qubits. So basically, these are the center qubits where the leaf spring is actually touching the top chip. So when we replaced it with a push pin, fixture, with the push pins located approximately on top of the hard stops, sure enough, we found the middle qubits with all the perfectly healthy resonators. And I have to say, it happened around half a year later. So there was some degradation in the coherences, and also we lost qubit 2 during the handling. But, but at least we found the center ones. Lastly, the qubit effective temperature. We constantly monitor it across all the cooldowns, and we always get around less than 100 millikelvin. And if we, spend more time on it, we can, put it more like at 54 millikelvin effective temperature of the qubits. So, in summary, the stable hard stops show promising resonator quality factors. Initial transmon characterization shows 10 microsecond average T1. We have good stability and predictability of the qubit readout coupling, and thermal excitation show effective temperature below 100 millik. And again, and I want to thank all the DiCarlo Lab team for discussions and support, and also the QTech technical support team. And thank you all for your attention.
Thank you, Matvey. Perfectly on time. Who has the cube there? Who wants to do the first question?
It's okay. Thank you.
Perfect.
Thank you for the talk. It's very interesting work you're presenting. I'd like to do a little more research on this mysterious disappear of qubits. Like when you say qubit number 3 and number 4 disappeared under the clamp you have. Yeah, this one. Yeah, first time saw that maybe is touching the field of the bottom side of the chip, but you have only 20 micrometers gap. Probably it's not the case. So do you think it's because of galvanic connection between the chips, so it's bowing so much that it's touching the bottom chip, or what's your idea?
I think not, because well, we were also, actually, I didn't show it here, but we actually tested the leaf spring, which was kind of, like circling around, like trying to avoid the qubits. And we actually were also able to see the qubits. So it's, well, it's more likely that they're just strongly coupled to the leaf spring, like electromagnetically. And then it's just losses.
And you sure you don't have bowing of the chip because of this spring? Because I think it would be the most concerning factor.
Well, yes, because, well, we kind of assume that if we get this nice flat, coupling strength, that we assume that at least, apart from the central qubits, the gap is stable.
Okay, thank you.
Time for another 2 questions, or actually 1. Oh, yeah, behind. Well, 2 questions, quick.
Thanks, it's very interesting. I was just wondering, when you assemble the 2 chips, how easy is it? Can you, do you use a normal microscope?
Oh, yeah, we use a kind of low magnification microscope.
Not a flip chip on.
Yeah, I mean, we actually, this is why we actually got this bottom hard stop so big, so that we can actually do it, just by hand. So we just put it somewhere around it, and then by gentle tapping, we can actually, sink one hard stop in, and then it's just rotation, and then all 3 are in, and then that's how we do it.
Sounds very.
Can you pass the mic? Thank you.
Hi, thanks for the great talk. On this qubit thermalization, is this 100 millikelvin compared against like a 50 millikelvin that you would expect standard in just a 2D architecture? Like, are you seeing excess noise just because of thermalization, or are there some issues with like the photon background?
No, I think we get the same for the normal, monolithic chips.
Yeah. Okay, great. So it's not a thermalization issue necessarily.
Yeah, it's weird that we never actually see the fridge temperature for the qubit's effective temperature, but that has always been the case. Sure. So it's
Thank you. Let's thank Matvey again.
Thank you.
So next speaker is Junction from Academia Sinica, and is going to show us the scaffold-assisted window junction for superconducting qubit fabrication. Thank you.
Okay, good morning, everyone. And I would like to thank for organizer to give us this chance to present our work. My name is Junction, and this is in a quite big collaboration with E3 Applied Material and Wisconsin, University of Wisconsin, and Colab. And perhaps a few keynote speaker and Jonas have talk about in terms of moving toward to the fault tolerance quantum computation, both quantity and quality of the qubits are pretty important. Unfortunately, we are kind of in 2025, now we are in a range of 100 of qubits each, which is pretty far from the industrial kind of expectation you want to reach to a million qubit in 2030s. And that's something we need to work on and make sure we can increase both the quantity of the qubit but maintain the quality of qubits. So to do so, we have to face a few issues. First of all, of course, we mentioned about loads. As keynote speakers mentioned about the surface oxide or surface amorphous create a lot of TOS loads to decrease the coherence time of your qubits. And these surface loads can come from three major interfaces, as we all know about substrate to metal, metal to air, and air to substrate, metal to air, and metal to substrate. And each of them have a different kind of weighting in terms of the participation ratio or loss tangent, etc. So to mitigate this kind of issue, to go beyond what currently we have fabricated in the lab, we have to think a better way to make sure the surface loss is less. Another key issue is making the junctions. Conventionally, we use the Manhattan kind of structure and Dolan bridge kind of structure. This kind of junction has a few key issues. For example, in terms of precision control in your EB lithography, to make sure your dimension can be well controlled, and therefore you can oxidize your barrier layer very well to control the frequency of your qubit, is a key for multiple qubit systems. And another issue is such a technology use so-called angle evaporation, which often create some polymer residue during the lifting off process, where you leave the strip of metal after the lifting off process, but nearby the strip of metal you may have contamination of residue of polymer due to the lithography procedures. And in another word, to control these area, critical dimension is not trivial, and control of these oxidation with the polymer nearby and reduce the TOS loss is not trivial. And in terms of that, we think about maybe use some semiconductor industry experience might be actually helpful in terms of better controlling the cleanliness of the device, as well as the critical dimension of my devices. And of course, we are not the only smart people. Jonas and the other groups also think about other way to do such a process. For example, IMEC was already using 12-inch production line to do such an overlap junction, as Jonas has mentioned, to reach to almost 100 microseconds T1 time. And in this process, they require to do a global cleaning, which you need to do bombarding away of the oxide layer to regrow the proper oxide in the beta vacuum chamber. And another way is doing tri-layer. So it's actually a penta-layer kind of structure from Stanford, from Schuster's group. In this case, one has to etch away such a device, which potentially use some silicon oxide kind of protection layer to make sure it protects your sample. And there's some tricky way to remove this kind of silicon oxide, which tend to decoherent your qubit later on. And a previous talk from Jonas already mentioned about this very brilliant idea using this tri-layer structure and oxide protect your tri-layer structure to make sure you can have a tri-layer qubit which works pretty nicely in his talk. And here we summarize a little bit different kind of methodology in here. So each way has its pros and cons. Of course, the leading in the coherence time still using the conventional overlap Manhattan junction or Durham bridge. But moving to a scale, we think better to use wafer scale kind of fabrication to ensure cleanliness and incorporating into a semiconductor ideas how we can make a better control in terms of critical dimensions. And another idea is we're trying to get rid of lift-off process to reduce the formless oxide or amorphous surface nearby our junctions. So to do that, we propose in the following ideas. So first of all, we have aluminum button electrode formations, and that can be done use both dry etching or wet etching processes on top of a high quality of silicon substrate. Later on, we deposit the silicon oxide and forming the protection layer on the bottom layer of the substrate to protect your substrate's air to surface and metal to air surface. And then we open up the via with two kinds of via. One is a junction window, the other one is a contact window. But contact window is just much larger, which then we can clean up this opening with gentle milling. Then we can regrow pristine oxide inside of these windows. Then we can put down the top electrode, as you can see in here. Then eventually we remove all the silicon scaffold afterward in the last step, which prevent all the contamination during the fabrication process that can cause to decoherent your qubits. And this has a few key features, like for example, we can eliminate all the lifting process, and the surface of your sample is well protected under the silicon oxide. Therefore, there's no contamination will left over after completely remove the scaffold. Idea is simple, but reality is not so simple. So the first thing we check is about removing the process, silicon oxide process. Does it work or not? And you can see from here, we play around with two different kinds of sample. One sample with the label of the dot. In here is a pristine silicon wafer with a resonator on top. So we check the resonator quality factor first. Then we also do the same design, the same similar round of sample with silicon oxide deposition on top, and then remove with the vapor HF. Then we check again with the resonator quality. You can see that the difference between two samples is very minimum. So could be in the round-to-round difference only. So after removing the silicon oxide, you can see the surface of your sample still remain pristine, and the interface remain very clean between the substrate and aluminum. And now turn to the part of fun part to create the Josephson junction based on this kind of structure. And you know, as an experiment, the first time you expect a bright future, but later on you found the etching end up like this, so it's not a very good idea. So we do play a lot of parameters to make sure the aluminum surface can remain pristine, and that first trial, of course, doesn't work. There's a residue and byproduct during the etching. But however, with the help of E3 and the collab, we found the proper recipe to etch your sample, etch the silicon oxide away properly, reveal the pristine aluminum grain without damaging it. And after that, you can do oxidation, etc. And there's an important thing we want to mention here is to control the critical dimension and the VRA angle is kind of important in our process because you want to fine-tune the etching recipe a bit to leave a little bit angle that allow you next top electrode properly contact to your sample. So there's a dimension dependence of angle, which we create a small TN image in here. On the other hand, if you check the critical dimension in entire 8-inch wafer, you found that using the industry kind of semiconducting fabrication, the critical dimension control is actually pretty well. Without any compensation in terms of exposure time, you can already reduce the dimension variation down to 2%. But we still found the central diameter at center still slightly larger than the edge, which can be compensated later on using the exposure time. And with that, we move to the oxidation steps. So we put down the oxide layer during the oxidation. In situ, we also put down the aluminum layer, as you can see from TN image here. So here we show the TN image with index of aluminum, silicon, oxygen, which luckily, as we expected, the elements are at their proper place. They didn't diffuse everywhere, etc. So we're also seeing a nice formation of oxide in between of the two top and bottom aluminums. And the oxide can be grown smoothly, and you can always analyze through the cut and the TN analysis to see nice formation of aluminum oxide in our barriers. And with that, we can finish off entire process by finally removing the silicon oxide scaffold. And you can see the tilt SEM image or zoom-in kind of structure. In this experiment, we actually test two kinds of different silicon oxide. One coming from the sputtering silicon oxide, the other coming from the PECVD core silicon oxide, which the sputtered silicon oxide you can see from the middle. Under the same cycle of VHF, we actually see very clean on the sputtered silicon oxide. Instead of PECVD oxide with the same cycle of VHF, there are a lot of residue left over in there. And that tells us important choice of silicon oxide that actually lead to different kind of results. That also come to corresponding to the decoherence time of your qubit. With leftover this residue, indeed we see much worse of a qubit coherence time. Instead of using sputtering silicon oxide, then the time can up to 57 microseconds. And with that, I would like to thank all the collaboration and from our collaborator from the collab, Wisconsin, and Applied Material E3. And if I may spare like one last minute, we want to introduce two new platforms in Taiwan, which we are open and welcome everybody to collaborate with us. So in the south of Taiwan, we are creating a new semantic center for quantum computing. And in there, we have two new platforms. And one first platform is using entire 8-inch process to create superconducting thin film and pattern thin film. And this clean room is dedicated for superconducting qubits only. So we can make different kind of structure, qubit fabrication, parametric amplifier, etc. And the other platform, in collaboration and partnership with many industry partners like Quantum Machine Collab, and software partners, we can actually have a very good support in testing the quantum chip or different kind of subsystem in our QC test center. And this center is open to all, so we are welcome to any kind of collaboration. Thank you.
Thank you, Junction. Time for questions. I've seen.
Thanks for a great talk. I think the previous speakers already mentioned that one of the problems with the Anfarov recipe was to etch away the silicon oxide without damaging the aluminum in the barrier. How do you do it? Because you have a lot of aluminum.
So from our side, we found that there's a quite different way how you etching away the silicon oxide. For example, there's a difference using solvent, or using different solvent, or using different vapor HF, etc. So that causes the result of damaging aluminum differently. Of course, we have not tried to compare, for example, sputter and evaporate aluminum difference, but so far we see the VHF has very little damage to aluminum.
Okay. I see somebody there. Yes.
Thank you for the talk again. Did you measure the junctions before removing the silicon oxide manifold? Did you see any difference between the VHF steps?
In this case, we do measure the critical current only. We didn't check the, intuitively think left the silicon oxide layer is not great, so we didn't actually check the coherence time with the silicon oxide on.
What was the change between the critical currents? So was it?
To be honest, we didn't see much of difference in the critical current. So in substratal current also not significant difference in the sense we don't think the barrier is, in terms of critical current, is influenced by the silicon oxide nearby.
Okay, thank you.
One last question.
Okay.
Very interesting talk. Many thanks. You said this scalability aspect for 2030, going more qubits and maintaining the quality. I'm thinking as well, or possibly a way is to have also these logical qubits. What I'm trying to see is that if I have a logical qubit and underneath, let's say, 10 or 100 or more qubits, what do you think are the key requirements? Which characteristics have to have the qubits to have a better logical qubit? Or is it about the resonators for the communication between the physical qubits? Or
it's a very big question. I think actually a lot of experts has a more right for me to answer this question. But I think in terms of quality of qubits, better coherence time and less of contamination is quite important. And another key we think is quite important is how you well control the frequency of your devices, which correlate to the barrier in terms of resistance of your structure. And therefore, moving on to the more semiconducting or industry-like of fabrication to make sure you can have a uniform distribution around entire inch wafer, we think is the key to make a large number of qubits. So you could have less than 100 microseconds of T1 time, but still Google can make a step toward to a fault tolerance quantum computation. And that's key important. That's a key to improve the quality of qubit and make sure the uniformity of qubit is really good. Yeah.
Let's thank the speaker again. And that's the end of the session.
Yes, great. We will be back here at 11:30. Great. And we are back for one more session before we go for lunch. And to present this session, we have Pranav Mundana from Q-Control.
Thanks, Christian. Hi, everyone. I'm Pranav. I'm from Q-Control. I head the hardware automation and integration department there, where we work on automating calibration and bring up of quantum devices, and also algorithmic error suppression for algorithmic advantage. So our first invited speaker in this Fluxonium session is Junction Deng. He's from Quantum Science Center, and he'll take us through the architectural considerations for Fluxonium qubits. So over to you.
Okay. Oh. Hello. Okay. Thank you. Going back. Okay, so good morning, everyone. So today I'm very honored to be invited here, especially at this place at Delft, to talk about our perspective and progress on Fluxonium qubits. So it is. I feel it's quite special to be visiting Delft, especially this is the place for actually the birthplace of the flux qubit. And in the first slide, so I would spend a little bit of time to introducing Fluxonium. For those people who work on the flux qubit for the long time. Okay, so it seems the resolution seems to be a little bit low, but maybe it doesn't matter. So, so Fluxonium is basically I would say it's a little bit alternative version of the flux qubit. So everybody familiar with transmons, so we have a Josephson junction and then a capacitors. So what's more here is that we added a shunted inductance to the circuit. So this circuit consists of all these essential elements for superconducting circuits: inductor, linear inductor, Josephson junction, and capacitors. And what it makes a Fluxonium is basically this kind of Hamiltonian, and then the parameter region where we have the Josephson energy greater than the charging energy and much greater than the inductance energy. So why is this parameter region important? If we plot the wave function of this qubit system, so we have this iconic double well potential, which is the feature of the flux qubit. But what make it different from flux qubit is that because of the EJ, which define the energy barrier of the two well, is so large, so that we have the first excited state and the ground state only separated by this suppressed tunneling amplitude, and then the rest of the energy states are considered to be like the plasmon energy excitations of this qubit, and like it's a harmonic oscillator like or transmon like states. So in combinations of this Fluxon tunneling and the plasmon excitations, that we have this very enharmonic energy spectrum, where the 0-1 state has a small gap, something around 100 megahertz, and then the higher energy levels are separated by a few gigahertz. So a very enharmonic energy spectrum. And what's more interesting for this qubit is that if we look at this dipole moment. So here I plot, so it's a little bit hard to read, but I walk you through. So here we have this charge. I plot the charge dipole moment of all the transitions, and then here I plot the magnetic flux or the magnetic dipole moment of all the transitions. So what's interesting is that if you look at this, the 0-1 transitions, though we have a very pretty much suppressed charge dipole moment, while the other transitions has large dipole moment. So it is easy to understand because the 0-1 transition is considered to be the fluxon tunneling of this of this qubit, and then it's the tunneling or the flip of flux quanta. So it's supposed to be suppressed in conjunction with charge dipole. So, and then if we look at this flux or the magnetic dipole, those things are very different. So we have this, it's kind of hard to read, but we have this magnetic dipole moment of this fluxon tunneling states to be a Stratham one. Okay, so keep in mind keep this energy spectrum and the dipole moment map in mind. So this will cover or help you understand most of the materials I'm going to through in this talk. So first, let's look at coherence. So because the charge dipole moment of the 0-1 transition is so small in Fluxonium system, we can engineer or achieve very high coherence times. So this is the qubit we make in our lab, and then we use this overlap junction technique that's more resilient or have a better wafer uniformities when we do fabrication at scale. So we make the qubit around 200 megahertz. So we select these particular frequencies to suppress the charge dipole moment. So we get the qubit basically more or less decoupled from most of these charge TLS to achieve such high coherence times at the millisecond level. So and then you might wonder, so people might wonder, then yeah, you make the qubit gap so small, so does it still act as a good qubit and still controllable, still be controllable? So here I would like to, so for single qubit gate, it's quite simple because that we just need to use direct microwave address the qubit splitting at 100 megahertz or a few hundred megahertz. Actually, this is easy because the frequency is low, and then we can address it using just direct the signal synthesis of low bandwidth AWG, something just like 1 gigasample per second. So for single qubit gate, we can directly address that, and then for the other operations, something like readout, and then we actually use the fact that the higher energy has a very strong charge dipole moment, so it couples the resonator strongly. And then for readout, we actually for the dispersive shift is actually given by the chi shift from 0-3 transitions and the resonator. So basically, the small gap doesn't forbid us to have a very, very large dispersive shift and then very good result. And then also, then we have to keep in mind that the qubit is so low in frequency, so then it gets thermally populated. So we have to do reset or always reset the qubit to do all the characterization. The way we do it in our lab is that we use this sideband cooling methods. So we ship the qubit away from the sweet spot, break the symmetry, and then allow these transitions directly from one state to the resonator state, enabled by these higher energy levels, and then assisted by these lossy readout resonators, and then we prepare the ground state with very high fidelity. Okay, so this is what we use, and then for it's actually quite a good scheme, because that if we really think about it, we can separate a bunch of interactions in very different frequency range. Say readout and reset are done in the gigahertz, a few gigahertz range, and then the qubit, single qubit gates are only in the hundreds of megahertz. So this is good for single qubit gate, and then the next it's for 2 qubit operations. So in our lab, so we spend time in trying so the most fundamental or elemental ways of coupling qubits. And the first one is the capacitive coupling. So that gives rise naturally the transverse interactions between the qubits, and then we can use it to implement I swap and square root I swap gates. And and then alternatively, we can also use it as use the inductive coupling to couple two qubits, and then they allow us to achieve native longitudinal interactions, and then achieve a very high fidelity CZ gate in a very short time scale. So let me expand a little bit and then and present you how does it work. So for capacitive coupling, so the things are pretty much similar to what people used to in the transmon qubit, and then the interaction is kind of like the YY or XX interaction, so that when we put two qubits on resonance each other, and then we can do these I-swap-like interactions. Depends on how long you keep this interaction on. So so this is the anti-crossing. Then we sweep both of the qubits into the same frequency, and then to do gate, and then we just need to apply the square pulses, and so pulse one of the qubit in frequency in resonance with the other, and then wait for the I-swap-like interactions to go on, and then switch off to complete the gate. So in this work, so we implement the I-swap gate within 50 nanoseconds, which is quite fast. And then we also do square root I-swap in roughly half of the time. So that's something around 20 to 30 nanoseconds, which is still pretty fast. So that's why we can get like something like 99.7 gate fidelity. But there are some caveats. So to be able to do this gate so fast, then we actually have to operate the qubit at a somewhat higher frequency. So basically higher than a gigahertz. And this has actually cost us some coherence time, especially T1, because from the previous slide I showed you, we have very good T1. That's originated from the very small charge dipole matrix element for the Fluxonium qubit. However, here then, because we want to couple two qubits using charge dipole, and then we have to boost this coupling strength in order to have a fast gate. So this sacrifices some T1, and then. And what's more that people don't like much is that it actually also introduces some ZZ residue interaction that's coming from the interactions from the higher energy levels. So remember from the first slides, the charge dipole from this higher energy state, or this plasma excitations are quite strong. So even though the qubit has very large enharmonicity, because the higher energy level are so strongly interact, so it introduces some residue ZZ that's non-negligible. Okay, so that's for the charge or capacitive coupling that we all familiar with. And then now, again, I want to mention is it's good to go back to Delft, because this is the birthplace of flux qubit. So flux qubit has been invented so long ago that people forget its properties, and also forget, so a lot of people also forget the Fluxonium is actually the flux qubit. So flux qubit has this property. So first, if we want to couple it, we can use its magnetic dipole, which is the conjugate of the flux charge dipole, and then but because of its flux qubit, so the magnetic dipole is actually very strong. So from this point, and it actually makes sense to couple a Fluxonium using a magnetic dipole, thus doing it inductively. Okay. This is one point, one motivation to use inductive coupling, and then the other one is that the Fluxonium or flux qubit has these very unique properties that when we tune the external flux, we not only tune this energy spectrum, we actually tune the angle or the energy eigenbasis with respect to the the basis we define. So for example, if we define the basis sigma z and sigma z as the circulating current basis as we used to in flux qubit, and then we can write the flux or the circulating current operator in this formula. So basically, we can tune the relative angle between this the energy eigenstasis versus basically we tune the relative angle of this flux operator or the current operator versus the energy eigenbasis. So basically tuning from sigma z to sigma x, which is a common thing that people do in flux qubit. So when we write this things down, so basically we couple if we couple two Fluxonium or flux qubit together with an inductive coupling, and then we write down the interaction Hamiltonian. We just need to expand the current operator terms, and then we suddenly get a bunch of very rich interactions. So here we get the standard x-axis interaction that give you swap-like operations. And then interestingly, we also get zx and xz that give you C0 interactions. And finally, we can actually get zz interactions that give you the cz interaction. So just by tuning the flux bias of these two Fluxonium qubits, so we suddenly open a box that allows you to do so many interesting things. So here the way we implement this qubit or this scheme is that we just have two Fluxonium qubits, and then in the middle, so we connect these two superconducting loops via a galvanic connection, Josephson junctions to boost the inductive interaction between the two qubits. So. Okay, so in this work, so we choose to use the ZZ interaction, so and then which is the native one that belongs to flux qubit and the Fluxonium. The way we enable this interaction is very simple. So we basically just need to turn on the flux pulses of both qubits at the same time. So what's happening is that we start at a 0-0 position. So basically both qubits at its spaceport flux degeneracy positions. And then we tune on the flux pulses at the same time for both qubits. And then we go to somewhere where we have this ZZ interaction that's large. And then we accumulate some phases, which is the two qubit phases give us the control phase rotation, and then we go back. So in this particular operations, so because the XX and the ZX interactions that has a faster rotating angle, so they average out because of the under RWA. So eventually we only get these C phase operations. And because the operation is so strong, so natively belongs to flux qubit, we can get the on-off ratio greater than 10 to the 3. I believe if we tune this the 0 point carefully, and then we can get an even higher level. So in particular in this work, and then we actually reach 99.6% fidelity with only 20 nanoseconds CZ. So this is blazing fast gate. Okay, so here is a brief review. So we try both of these conjugate coupling schemes for Fluxonium qubits, and then for capacitive coupling, so we kind of run into the trade-off between whether we need to fastgate or the high coherence because the charge dipole moment of this qubit it's small. At the same time, we also, if we want to boost the charge dipole moment, and then we actually also suffer from higher residue couplings because of this even stronger coupling path from these higher excited states. Okay, but the good thing is that this design resembles that of the transmon qubit. So we learn the tricks from transmon, so we can have isolated qubit design and then low crosstalk. On the other hand, so it's we also tried this capacity or inductive coupling that allows us to couple both qubits very strongly. So we have fast gate because they have rather than using the charge dipole, they use a magnetic dipole, which is very strong for flux qubit or Fluxonium. And then we have fast gate and a small residue ZZ, which is very good. However, so one thing that I haven't mentioned in the previous slide is that we also have a lot of problems to address. One thing is that to have this strong coupling, we have used galvanic connection. That gives us some stray modes in the circuit, which is very hard to deal with. And then also another nightmare is that this circuit has very high flux crosstalk that it might impose a huge problem when we scale to multi-qubits. So, so basically, it seems that there's no perfect solution. However, we have to remind ourselves that such analysis only conserve ourselves in the computational basis. So if we go back to this very blurry charge dipole diagram, so we can. And we all like to couple qubit using charge dipole because they are well isolated and easy to control, easy to design, right? So we still have this qubit computational space charge dipole small. However, we have this. So this is. This is 1 to 2 transitions, and then this is 0 to 3 transitions. So these transitions, however, are pretty strong. So then people figured out how to use it. So, for example, in this paper published by the Maryland group, so they actually figure out that because of this transition is so strong that the level repulsion between the 2-1 and 1-2 states are very useful. And then this level repulsion breaks the degeneracy between these two transitions so that one can directly use microwave to drive one of those transitions without exciting the other. And then selectively drive this transition will excite the state from 1-1 to up and then go back and pick up a pi phase shift on the 1-1 state that give you a C phase gate. Okay, so this is the way it seems to be good to go around to using the very strong coupling between the non-computational states. And then later, so people from MIT, and then this is from the RQC, they go further to introduce tunable coupling schemes, a tunable coupler. So here is a transmon, and here is a Fluxonium to basically achieve a very small ZZ, and then and also low crosstalk and isolated qubits, and then very high gate fidelity. So still, there's still some drawbacks. So then because we use these higher levels, and then we have to suffer from this relatively short lifetime of those levels, and then we need to deal with the leakage. But since there's no perfect solutions, there's no free lunch, and then we find that this is probably the scheme we should go. And then we feel that the shortcomings can be addressed over the way. So here I want to present you a scheme so we envision for scaling up a Fluxonium processor. So here I just draw like 5 qubits in a row, and then first the coherence times. Single qubit gate can be addressed by just directly driving this low energy manifold. So this can be done with very standard AWG. And then we put the radar resonator here. So basically we enjoy a strong dispersive shift contributed from this 1-2 and then the 0-1 transition. Okay. And then to do reset and leakage removal, so what we can do is that we move this 2 state in resonance with the resonators to exchange it to remove all this leakage, and then also we drive these transitions to transfer the sideband, so do the sideband cooling, so transfer all the populations in one state to the resonator and then go back to the ground state. So for 2-qubit operations, so we have two choice of parameters. So one is that we can use these 1-2 transitions to enable the 2-qubit gates. So the way we do it is that first we packed the coupler on a very high frequency, so they essentially turned off all these qubit-qubit interactions. And then when we want this interaction, so we on demand pull the coupler down to the frequency with respect to the 1-2 transition. So in these schemes, one way to understand this scheme is that you can completely forget about the 0-1 transition. Just think about this 1-2 transition as a transmon qubit. And then we bring the transmon coupler down or in near resonance, so they basically we open the interactions between the two states, and then we have this level repulsion allow us to do this microwave activated gate to accumulate the phase shift, and then the 2-qubit gate can be done. And what's more is that we have another set of parameters that we can, which is corresponding to the 0-3 frequency, so we can perform another set of the 2-qubit gates. Okay, so that's enough for analysis. So this is to give you some data to show you that this is really working. So we fabricate a chip, and then we take the 4-qubit subgroup, and then here this is the qubit parameters. Then we run simultaneously randomized benchmarking for single qubit gates, and then you can see that this is parallel single qubit gate, and you can see that the fidelity is approaching 4.9. Even some of the qubits are very close in frequency. So basically that shows that the crosstalk between qubits are really negligible. And also the parallel 2-qubit gates can be implemented in the scheme I showed you earlier. And then here we reach average gate fidelity above 2.9. And then we try to look into the detail a little bit more to see what's the limitations. So we basically select a good pair of qubit where it experiences relatively good coherence times, and then we shorten the gate lengths to something like 32 nanoseconds, and then we also decide to park the qubit on the idle position, on the always-on idle positions, to eliminate some of the pulse pedaling times that we have to tune when we have to tune the flux. We find that we can actually push the fidelity to 3.9. So basically that means that there's still a lot of rooms for optimization. So finally, so this is still the work in progress. So just to show you that we are working on a bigger chip. So we fabricate a processor we call Lotus, fully made of Fluxonium qubits and then transmon couplers. It has 22 qubits in the chain. So we already have more than 3.9 single qubit gate fidelity in parallel, and a little bit above 95% fidelity in 2-qubit gates. So next, as I just mentioned earlier, so it's useful and motivated to try alternative pulse schemes so that we can avoid some of the pulse distortions and problems when we move in the couplers from very high frequency to the target frequency. And then Chris showed that group showed that adding a little bit of optimal control is very useful to eliminate some of the unwanted transitions and leakage that might help. And then maybe I would say maybe the most important thing is that on the bigger scale chip, it's always challenging and tricky to balance coherence time and qubit yield. So they basically we have to keep working on that to find a good balance to achieve both quantity and quality. And finally, so we have some idea on the 2D grid topology, and then we think it should work as long as we have the good trick to deal with this capacitive loading problem, because from 1D to 2D, you suddenly jump from a 2-neighbor to a 4-neighbor cases. So this is the challenges we're going to address next. Okay. Finally, so if you want to know more about our institution, so it's a very long name, so I want to make it simple. So it's Quantum Science Center of the Greater Bay Area. So the URL is QSCGBA. So it's easier to remember. Otherwise, it's so long, and then you can check the website and then see our lab and the open positions. Thank you.
All right, time for 2 questions.
Thank you for your presentation. I have a question about the 2-qubit fidelities for the 1D chain, because there you saw that the single qubit gates were pretty much the same as the previously reported values at 99.9 average, but the 2-qubit gate fidelities dropped to 95%. What was the main reason why the 2-qubit gates dropped, but not necessarily the single qubit gates?
Okay, so for this particular chip, then we blame the coherence. So then we didn't have as good as coherence as the other processors in this chip. Yeah.
Can I ask a follow-up question, or do I pass it to?
Sure, quick question.
So then you mean you have worse T2s off sweet spot when you do the coupling or something, or why does the coherence affect 2-qubit gates more than the single qubit gates?
Okay, so I will put it like this. So because in this particular chip, so we designed the transmon coupler to be idle at pretty high frequency. So and then we need to, so we have this on position and off position that's different by I would say like 4 gigahertz. So that requires us to bring the coupler all the way to the operational point from the idle point, and then in the middle, so the flux sensitivity is a little bit high. So and then we basically have this trade-off to whether you want to operate it at a sweet spot for the coupler, or you want to operate it at a point that you have the maximum coupling but lower coherence times. Okay. So basically, there's a little bit of trade-off.
That makes sense. Thank you for your explanation.
Maybe one more question. Can you throw?
Okay, thank you very much for the talk. So my question is regarding the inductive coupling between the 2 fluxoniums. You mentioned that you have some stray modes because of the galvanic coupling. And then my question is how critical you find these modes, or if you have thought of any workaround.
Okay. So the question is about the stray mode, right?
Yes.
Okay. Actually, we have a workaround in this particular device because just to show you, there is a stray mode because all these nodes has to connect to the capacitance, straight capacitance to the ground. So basically, there will be an extra stray mode oscillating from this point to this point. It's a clock oscillating mode like this. However, this mode would not couple to the qubit if everything is symmetric. So the way we mitigate that in this particular device is that we make it very symmetric. However, you can envision that it's very difficult to make it to keep this symmetric when you want to extend to a grid with multiple qubits.
Okay, thank you.
Great. Let's thank our speaker again.
Thank you.
Okay, next speaker is Vivek Moria from University of Southern California, and he'll talk about a compact planar multimodal device for efficient error suppression encoding.
Hello. Hi. Yeah, that's a pretty elaborate title. So yeah, I'll be talking about a compact planar multimodal device which can be used for error suppression and encoding. So to start with, yesterday was all about error correction. And what we learned is error correction is great, but only if you are below a certain threshold. So, and most of our community is trying to bring down these logical error rates. by using these techniques. These are not exhaustive, but people generally use decoherence-free subspaces, erasure qubits, or bosonic encodings. And a few of the most important ingredients to do these things are higher dimensional Hilbert spaces. We need to have good logical space readout, and we need to have flexible and high fidelity control in the logical space. Now, you can use a couple of transmons and then couple them together and use that as a modular element and get the first two things right. But the third thing, especially for fast multi-qubit gates, when you try to increase the coupling strength of the coupler, then you go into this issue of higher crosstalk and spectator errors, and that becomes a problem. So there is a need to study, there's a need for a device to study these kinds of things. So before discussing the device, I'll be discussing dispersive coupling, which is at the heart of the device. So this is a Hamiltonian of 2 qubits, which are coupled via ZZ coupling and with a coupling strength J. As you can see, this coupling strength J does not change the eigenstates of the system, but it changes only the eigenfrequencies. So now the frequency of each qubit will depend on the occupation of the other qubit. So we can see that in this level diagram here, frequency of qubit A when qubit B is in 0 state will be omega A minus 2j, but frequency of qubit A when B is in 1 will be omega A plus 2j. So there is a difference of 4j. Similarly for qubit B as well. So in this kind of system, C0 gates are native. So let's say I want to play a C0 gate conditioned on C0 gate on B, conditioned on A being in 1, then I'll just have to play this one pulse here, and I'll be able to get my C0 gate. For a NOT gate, I just have to play opposite control condition on qubit A, and I'll be able to get a NOT gate. And I can play this pulse either sequentially or simultaneously. So we can use direct microwave radiation to do 1 or 2 qubit gates. Now, back in the day, Vijay's group at TIFR came up with this 3D version of a device called Trimon. So the circuit schematic looks like this. So this looks complicated, but this essentially is a combination of 4 transmon-like circuits given like this, which are strongly coupled together by these capacitances, CA and CB. The way we realize this in chip is by these large capacitor pads. Capacitor 1 and 3 gave rise to CA, and 2 and 4 gave rise to CB. Now, this system is actually very similar to a coupled system of 4 spring and masses. And from classical mechanics, we might remember that this system has 3 normal modes, which look like this. The masses move in this fashion. Whereas the 4th mode will be a degenerate mode, where all masses will move in the same direction. So that will have no frequency. So we get a similar structure for a similar mode structure for our Trimon as well. So we have a dipolar qubit mode A, where EM fields oscillate in pad 1 and 3, and the colors show the direction of oscillation. So we have a dipolar qubit mode B, where oscillation happens in pad 2 and 4, and we have a quadrupolar qubit C, where EM field oscillates in all 4 pads. Now, let's look at the Hamiltonian of the circuit. So it's a pretty simple Hamiltonian, where you have the usual transmon-like terms. You have the qubit frequency, you have the anharmonicity, and you have self-Kerr term, J mu nu. And here n are not the charge operators, those are the number operators. So as you can see, the coupling strengths are pretty similar to what we have in transmons. And if you calculate the frequency of each qubit, you will see that it will now depend on the state of its partner qubit. So each qubit will have 4 different frequencies, depending on the state of the other 2 qubits. So it's easier to understand it in the level diagram. So we have 3 qubits in total. So we'll have 2 to the 3, 8 levels. We start with qubit C. When A and B are in 0, will be this arrow here, and similarly the other 3 transition will be this. Similarly for qubit A and B as well. So you have in total 12 transitions. So in this kind of system, C0 gates will be native. So let's say I want to play a C0 gate on qubit C conditioned on A and B being in 1. Then I'll just have to play this one pulse, omega CA1B1, and I'll be able to get a C0 gate. Similarly, if I want to play a C0 gate, what I'll have to do is I'll just have to play opposite control conditions on qubit A, basically play these two pulses here, and I'll be able to get a C0 gate. And this can be simultaneous as well, because the transition matrix are block diagonal. And in order to play in order to do a NOT gate, what I'll have to do is I'll just have to play all these four pulses together, and I'll be able to get a NOT gate. Now, this is how the planar version of the device looks like. So we have this is a microscope image of the device. We have a transmission line at the bottom. We have a trimon at the center, and at the center of which we have the 4 Junction junctions of the trimon. And we have a charge line through which we can directly drive the trimon. And as you can see, this is pretty far separated because we wanted to make sure our T1 and T2 are not limited by that. But we can make it much more closer now that we know that it's not limiting. And we have resonator 1, which primarily couples to mode A of the resonator. We have resonator 2, which strongly couples to mode B of the resonator, and mode C couples to both the resonators. So we can use joint readout of 2 resonators to distinguish our 8 levels. So these are some experimental results that we have. So as I've discussed, the charge line allows us to drive faster. So this is an example of 14 nanosecond CC0 gate with 3 nines fidelity. And this clearly is coherence limited. So if we can make our fab better, we can get better fidelities as well. And we can implement a C0 or NOT gate with simultaneous CC0s. And we could get up to 99.88% fidelity for simultaneous CC0s. But we can improve it by improving our calibration techniques, basically. And these are results for other qubits as well. Now, let's say I want to prepare a belt state in the system. What I need to do is, let's say I start with the ground state 0, 0, 0. And then I play a pi/2 pulse at omega A B0 C0. So this brings half of the population to 1, 0, 0. And then I can just play a pi pulse to invert this 1, 0 to 1, 1. And what I'll effectively get is a belt state on the first 2 qubits. Now, we did the exact same experiment, and here's the belt state tomography. You can see that it could get near 1 concurrence and greater than 99% fidelity on 5+. Similarly, for Psi+ as well, it could get very good fidelities. And you can see most of the errors is incoherent part. And similarly, for other belt states as well, we were very close to 1 concurrence and greater than 99% fidelity. So one more thing that you can do here is you can do Raman transitions. So you might know that a Fredkin gate or a C-swap gate effectively takes 5 C-naughts or 3 C-C-naughts to implement. But by driving Raman transitions, you can do a Fredkin or a C-swap gate with just 1 effective pulse. How do you do that? So let's say I have a level structure like this. What I do is I drive these 2 transitions with a detuning delta from 0, 0, 0. Then I can adiabatically transfer population from 1, 0, 0 to 0, 1, 0. And this is what is called a Raman transition. And there will be no transition here because there is a detuning. And there are certain conditions that you have to follow, but if you do it right, you can actually do it. So this is the experiment we did. So we initialized the state in 1, 0, 0 first. And then we played these 2 pulses together. And we swept the amplitude of these 2 pulses. And then we did the readout. As you can see, we started with 1, 0 population. And all the population got transferred to 0, 1. And the leakage was minimal. And we did the state tomography on this as well. And we could get 98.2% fidelity for a C-swap and 99.3 for a C-square root swap gate. Now, one last thing that I wanted to talk about is how we can use a trimon as a qudit. So consider an example where I've chosen these 3 arbitrary levels inside the trimon, 100, 000, and 010. And I'm calling this my qtrit. Now, I can run a usual Ramsey kind of experiment in such a system. What I do is I prepare a superposition state, basically a superposition of all 3 levels. And then I wait for a time t. And then I unprepare the state, and I do the readout. What do you see? You see usual oscillation, like you see in a typical Ramsey experiment. Now, what I can do is I can play a DD pulse here, equivalent to an echo for a qubit. So I just insert 3 X pulses in between with equal spacing. And this is equivalent to echo, where you play 2 X pulses with equal spacing. And what do you see here? You see no oscillation, and you get like more than 2x improvement in the decay time. And you can play this game for a Q-quart as well. I've done the same thing here. This is the Ramsey-like curve, and then this is where I've played DD pulses, and it becomes oscillation-free. And then you can do this for qudit for d is equal to 6, 7, 8, so on. So all in all, we saw that longitudinal coupling can implement multi-qubit gates better. And since our trimon is one single structure, this all 3 qubits are inside this. So all 3 modes share a common mode noise. Like whatever noise is will be there is going to affect 3 modes together. So this is a great platform to study decoherence-free subspaces where you need some kind of symmetry in the noise. You need some kind of symmetry in order to cancel the noise. You don't typically get it in a conventional transmons, because transmons are usually far apart and they are coupled by a coupler. So there is usually no common mode noise due to the weak coupling. And then presence of fast multi-qubit gates and flexible readout allows us to encode information in erasure qubits as well. I have not discussed this, but then we are trying to do more experiment in this point. And so all in all, this is a great platform to study error suppression and encoding. Thank you. Okay.
Hey, thanks for the talk. Yeah, it's really nice, the longitudinal coupling. I used to work on superconducting spin qubits, which also kind of have this native longitudinal interaction. But what I was missing was, how do you turn it off? Because now you are continuously doing CZ gates on all your qubits, right?
No, you don't need to turn it off, actually. The transitions. So usually in transmons, you have the residual ZZ coupling, and you have to correct for those. Here, the transition, already has those ZZ included in them, and it's pretty large. It's like 300, 400 megahertz. So all your transition energies will be different, and they will be in a rotating frame, inside a rotating frame. So if you work out the theory, you will see that it works. Like you don't have to correct for it.
Okay, yeah, I thought you keep getting conditional phases, but maybe you're right.
Yeah.
Yeah, okay.
For the talk. My question is about how do you envision using them as, say, qtrits or encoded qubits, and then making multiple of them talk to each other? So at the moment, if you have two trimons, it doesn't seem like it's trivial to design a coupling that's meaningful or coherent, effective, I guess.
Yeah, that's a great question. So what we are envisioning is basically you have a trimon, and you use that as a modular element. Let's say you encode 1 qubit in that full trimon, and then you can talk to another trimon using a usual, let's say how you do transmon gates, basically, like either cross resonance or like tunable couplers. And what we are selling is basically encoding single bit or 2 qubit information inside a trimon, and then you can talk to other like other structures. And the other structure can be a transmon, it can be another trimon, and the coupling will look pretty similar. Because ideally, trimon, like I'm calling it a trimon, but transmon is a monomon, basically, right? So yeah, you can couple them using conventional couplers. And yeah. It'll be a design challenge because you will get like level crossings and all, but like yeah, you like in theory you can do it.
Thank you.
Okay. Okay, let's thank our speaker. Okay, our last speaker for this session is Martin Swansberg from TU Delft, and he will talk about single qubit gates beyond rotating wave approximation for strongly anharmonic low frequency qubits.
Yes. Yes, thank you very much for the introduction. That's a very long title, so let's start from the basics. The Hamiltonian describing single qubit gates generally consists of two terms. The first term comes from your qubit, which in our case is a Fluxonium superconducting qubit, consisting of a capacitor, a Josephson junction, and a linear inductor, all shunted in parallel. And this qubit has already been discussed in much more detail by the first speaker of this session. The second term describes your drive signal, and it consists of a pulse envelope, in this case a cosine, and it's multiplied by a carrier signal. And this pulse is completely parameterized by two free parameters. There's a drive strength, capital omega, and a drive frequency, omega d. What's important is that this drive signal represents a linearly polarized drive signal. And that means that it actually consists of two components, which I've tried to color code with the red and green colors on this slide and sketched on this block sphere. The first component rotates in the same direction as your qubit, which we call the co-rotating term, and the second term rotates in the opposite direction, which we call the counter-rotating term. So now that we understand the components of this Hamiltonian, let's derive the time evolution. And for this, we need to take two steps. First, we go into a rotating frame, such that the qubit and co-rotating term become stationary, and the counter-rotating term rotates twice as fast. We then invoke the rotating wave approximation, or RWA, and drop the counter-rotating term, such that we're left with a system for which we can analytically solve the time evolution. Importantly, the RWA is valid only if the drive strength is much, much smaller than the drive frequency. But for Fluxonium qubits, both the drive strength and the drive frequency can be on the order of 100 megahertz. So it's clear that the RWA really doesn't hold for Fluxonium qubits, and that we cannot drop the counter-rotating term from the Hamiltonian. So the key question that we wanted to answer in this work is what type of errors arise from the counter-rotating term, and more importantly, how can we correct for them? Specifically, two challenges arise. First, it's once again challenging to compute the time evolution analytically, because remember, that's the original motivation for the RWA. And secondly, the time evolution will now depend on the absolute time at which you apply your gate. Now, let me elaborate on that a little bit more. Let's pretend that this sketch represents the first gate that we apply, and we now immediately apply a second gate. During this second gate, the counter-rotating term will make the same number of precessions as in the first gate, but crucially, it has a different starting phase. And that means that this counter-rotating term induces different errors in both of these gates. And that makes these non-RWA errors, as we call them, very challenging to correct. However, what we show in our work is if you do a sufficient amount of math, that you can actually derive a term that corrects for these errors in a first-order approximation. And this correction involves adding an out-of-phase component to your drive. So that means that there's a second pulse envelope, which in this case is the time derivative of the in-phase pulse envelope, with the second drive strength lambda, and it's multiplied by a second drive signal, which is 90 degrees out of phase with our first one. And to some of you, this might sound familiar, because this is also how drag pulses are implemented in transmons. But I wish to emphasize that not only our derivation, but also the errors that we correct for are fundamentally distinct. So next, we should ask ourselves whether these non-RWA errors are the only errors that we expect in our Fluxonium qubit. And the answer is no. The Fluxonium is an example of a strongly enharmonic system, and I've sketched the energy level diagram of a typical Fluxonium here on the slide. The Fluxonium typically has a relatively large enharmonicity. It's typically several gigahertz, which is an order of magnitude larger than for transmons. And this provides the Fluxonium with a very natural way to suppress leakage. But it doesn't mean that we can forget about the non-computational levels altogether. Because when we apply single qubit gates, we of course don't only drive the 0-1 transition, but we drive transitions between all the levels that couple to each other. And the reason that these non-computational levels can still influence the qubit dynamics is because they couple very strongly to our computational subspace. To be a little bit more specific, in this work we focus on charge driving, and for the Fluxonium, the charge matrix elements of the 1-2 and 0-3 transitions are about an order of magnitude larger than the charge matrix element of the 0-1 transition. What we show in our work is that you can correct for the errors that come from this by adding a time-dependent detuning to your drive frequency. So this now gives us 4 parameters in this pulse. There are the 2 drive strengths, omega and lambda. There's the drive frequency, and now this time-dependent detuning delta. But what we actually found in our work is that the optimal values of all of these parameters depend very strongly on your desired rotation angle. And because we decompose our native gate set in both pi-on-2 and pi pulses, that means that we actually have 8 parameters that we need to calibrate. So the next question that we wanted to answer is, how can you do this in an actual experiment? In other words, how can you minimize the error in some experimental setting as a function of all of these pulse parameters? One way in which this is commonly done is by implementing a calibration protocol named Orbit. Orbit directly implements a classical minimization algorithm on your measurement computer, which will then minimize some experimentally obtained proxy for the gate error as a function of your pulse parameters. So using this minimization algorithm and the pulse shapes developed in this work, Orbit will then correct for the non-RWA errors and for the errors from non-computational levels, which I've abbreviated as NCLs here. However, Orbit has 2 serious drawbacks. First, it's very resource intensive. It typically requires running tens of thousands of circuits on your hardware. And secondly, Orbit is non-deterministic in the sense that if you run it, you're not guaranteed to find the optimal pulse parameters. And this happens because this minimization algorithm could get stuck in a local minimum or might not converge at all. And this really motivates the search for different calibration protocols that do not have these drawbacks. And in our work, we formulated one such calibration protocol, which, for lack of a better name, we just refer to as the deterministic calibration protocol. And this protocol really makes use of the fact that these non-RWA errors should be completely determined by the shape of your pulse, which in turn is determined by me, the experimenter. In other words, the ideal correction term should not depend on any system parameters, such as precise transition frequencies or coupling strengths. And that means that we should be able to predetermine the optimal correction term. And experimentally, we therefore only calibrate for the non-computational levels, which significantly reduces the amount of circuits that you need to run to about 100, which is similar to conventional calibration protocols for transmons, and that then makes this calibration protocol deterministic. And that's exactly what we want. So now let me show you the device on which we implemented these calibration protocols. The device consisted of 2 Fluxonium qubits, shown in blue, coupled by a transmon, shown in green. And both Fluxoniums had their own charge line, flux bias line, and readout line. And in this work, we focused on only one of the Fluxonium qubits, which had a qubit frequency of 99 megahertz, an enharmonicity of 4.2 gigahertz, and T1 and T2 echo times of 75 and 37 microseconds, respectively. So now let's go to our experimental results. In this figure, I'm plotting the error on the y-axis as a function of the gauge duration on the x-axis. Notice that on the top x-axis, I've plotted the ratio between the drive strength and the drive frequency as a measure of how valid, or invalid in this case, the RWA is. And I've started by plotting the coherence limit, which is the minimum error we can achieve just based on decoherence processes. Next, we would like to know the minimum error that we can achieve in this experiment specifically. And we do that by measuring the amount of incoherent errors in our gates using purely randomized benchmarking. In an ideal experiment, the dashed line should coincide with the solid line, because decoherence processes are typically the only source of incoherent errors in your gates. However, in our experiment, we suffered from heating from our microwave pulses, which causes this discrepancy. So before implementing the calibration protocols that I introduced 2 slides ago, let's do something far more simple. Let's assume that there are no errors, and let's just implement a simple cosine pulse envelope. And if we do this, we see that the error is clearly not limited by the incoherent errors, indicating that there are other errors in our gates that we should correct for. Next, we implement our deterministic calibration protocol, and we see that now for 4 of the 5 gate durations, the error is completely limited by the incoherent error. We therefore implement orbit only for the shortest gate duration, where it manages to reduce the total error. So now, to understand what limits these errors, we numerically computed an error budget, which I'll show here only for the 26.7 nanosecond gate duration. What's important is that these error budgets only take into account the coherent errors. And I've started by plotting our experimentally obtained estimate of this coherent error. So next, we numerically compute the contribution to this total coherent error from non-RWA errors and from the non-computational levels. And what we see is that if we assume that there are actually no errors, then the coherent errors split almost 50-50 between these 2 categories. Next, we see that our deterministic calibration protocol reduces the coherent error by more than 3 orders of magnitude in both of these categories and achieves a total coherent error below 10 to the minus 6. Even though we didn't experimentally implement orbit for this gate duration, we did simulate it numerically, and we see that the total coherent error that it achieves is similar to our deterministic calibration protocol. Finally, we also simulated the leakage rate for these system parameters, and we found that was negligible for this gate duration. So that brings me to the conclusion of this talk. In this work, we've derived 2 correction terms. One that corrects for the counter-rotating term in the Hamiltonian, and one that corrects for the non-computational levels of a Fluxonium qubit. We implemented these correction terms experimentally on a Fluxonium qubit, and we found that they were very effective at suppressing the coherent error far into a regime where the RWA doesn't hold. And our numerics indicate that in this regime, we can achieve total coherent errors that are below 10 to the minus 6. And with that, I would like to thank the team. And if you're interested in other work that we do in our group, I can highly recommend any of these posters. Thank you.
Questions? Maybe I can start.
Oh, there's one there.
Sorry.
Oh, there as well.
Yeah. Did you either simulate or measure how this ability of your method to correct for the non-RWA error scales with the power or the strength of the driving?
So with the strength of the driving, so there's really kind of a cutoff where at some point the error becomes, let's say, above 10 to the minus 6, and it will increase exponentially with the drive strength.
Right, so there's a strict upper limit.
Yes. Yes, so there's really an upper limit in terms of the drive strength or gate duration, yeah.
Hi, thanks for the nice talk. For your purity benchmarking in the sequence, were you using the deterministically optimized pulse sequences or the no error pulse sequences?
Yes, that's a good question. We tried all of them, and the results didn't change.
Okay, you did see that it was independent, so there was no higher order correlated thing breaking down the protocol or anything like that.
So there is something that breaks down, but we can discuss about it outside because it's a very lengthy explanation.
Yeah. Okay, great.
Thanks for the talk. So in the end, what does your pulse shape actually look like? So for your deterministic pulse, does this look very different to the orbit pulse, or do they look quite similar?
That's a good question. I haven't checked the precise actual pulse shapes, but they will definitely look very similar because the final pulse parameters are super similar. So they yeah.
Okay, thank you.
Great. Let's thank our speaker.
And for some practical information, I will invite Amber from Orange Quantum to say a few practical notices.
Thanks, Christian. Perfect. Right, so Christian focuses on the substance, and I get the honor to also share some logistical details with you. Some things change during the day, and then we have to give you an update without that it's in the slide. Right, we go into the afternoon, and later at 1:30, we will use the stage for the first posters, which will give you a backstage view into the science, sticking with the theme of the theater. So feel free to then come into this room, use the stairs, and the posters will be here prepared. For the workshops, they are not in this location. They will be in the Pathé, which is the cinema next door. You will go out of the venue in the front entrance and go to the right. And it should be obvious where the cinema is. And you will be guided by our volunteers. Some details on the workshops I do have to share with you, so bear with me for a moment. There were 2 registration moments that some people have seen. There was an expression of interest first, where you could indicate which workshop or side event you could join, and there was an actual registration afterwards with a link that you received through the email. That registration was the one that closed yesterday. We will let in first people that did this second registration, the real registration. Please show when you enter your badge to the volunteers that are checking who gets in. And if you're not immediately in, please queue in front of the workshop so that when it's filled up with the people that registered, we can hopefully still let you in. We expect that there will be enough room for most workshops. Then I would also like to ask you, there are 2 consequent workshops following each other, to leave the room after each workshop, so in between the 2 workshops. So we can, again, give priority for the people that signed up for the workshops in the same system where you entered in the first place. Then just highlighting the workshops that will happen in parallel to the poster sessions. 2 are happening at 1:30. Quantum machines will be in Pathé in room 5, Zurich Instruments and River Lane in room 7. And the second batch of workshops at 2:30 will be Q-Blocks in room 5, IQM in room 6, and Cruise in room 7. It will also be clearly indicated at the entrance of the rooms. And then a last one, if I still have a minute, for the bikes. There are about half of the reserved bikes are still not picked up. And we think that's kind of a shame, because it's a really nice way to get around in Delft. So if you did reserve a bike, if you still remember, please pick it up during the lunch. By 3 o'clock, we will start giving it out to people that haven't booked them in advance. So then you might lose access to your registered bike. So please do go through the lunch to my colleague from Orange QS, Andrea, who will be at the registration desk, if you want to pick up your bike. I highly advise it. It's a great way to get to the other side events later today and the rest of the week. That's it for me. Then lunch will be served outside here. And don't forget, there is a summer terrace outside, supported by Moods. There's also even Wi-Fi there, if you want to have a quick call with someone or have a meeting.
Yes. Thank you, Amber. The excursions and events will start after this session. So whenever we are done with this session, we will meet up and we will just go to the events, and they will all be synchronized to whenever we are done here. So the information will come for that. With that, I will give the word to the chair of the session, which is Chris Freund from Niels Bohr Institute.
Great. Hello, everybody. I hope you all had a good session previously with the posters. I'm Chris Warren. I'm a research scientist at the Niels Bohr Institute Novo Nordisk Quantum Computing Program, and today I'm going to be the chair. So today we're going to be focusing on superconducting qubits and algorithms, and it's my pleasure to introduce Alba Sverlieta from the Barcelona Supercomputing Center, where she's an established researcher. And today she's going to be talking about quantum HPC integration and the challenges and opportunities associated with it. So please give it up a hand for Alba.
Thank you. Hello? Yeah. Thank you, Chris, and thank you, the organizers, for inviting me to give this talk. And I would like to give an overview of what a supercomputing center like ours is working on in quantum computing, and in particular in superconducting circuits, because the devices that we have installed are superconducting circuits precisely. Okay, so this is the outlook of my talk. So of course, quantum computers are a type of computer. Therefore, it has sense for a supercomputing center like ours to install these kind of devices and to integrate them with the rest of the infrastructure, which is a supercomputer, a traditional supercomputer. And how can we do that? So the first challenge, of course, is the installation. And the first thing to take into account is that a supercomputing center is not a lab, it's a site, it's an operational site. Therefore, it shouldn't be operated by experimentalists, but actually by technicians, the same technicians that take care of HPC. Of course, this is a big challenge. It's not obvious how to do that, but this is very important if you are planning to sell or to install a quantum computer in a center like ours. The second thing is the integration. So how can we connect this quantum computer with the rest of the supercomputer infrastructure? There are many things that we can discuss about integration, but in my talk, I will address the particular challenge of the task schedulers and the workflows that are needed to execute these hybrid algorithms. And for that, we presented the QD-Sleep, which is a particular library that is based on a task manager software. Then there is all the testing and validation that is so important for ours, to not only to provide the necessary tools to the users and the necessary information to the users about the quantum computing system, but also to check ourselves if the quantum computer is working properly, if we need to upgrade it, if we need to replace any part, and so on. And for that, I will present one particular benchmarking measure that you can use, which is the generation of highly entangled states called absolutely maximal entangled states. And finally, I will briefly review an application, which is high-dimensional non-locality. So in particular, the generation of high-dimensional Q-treated states with superconducting circuits, which is not related with HPC, but I wanted to show this example as one of the applications that a device that can run more than 2 levels can have. So let me start. So why a supercomputing center is interested in quantum computing research? Of course, the first thing is because we explore new ways of computation, and we like computers, and we explore what are the capabilities of those computers. And as you know, traditional computation is reaching its limits. We are saturating this Moore's law. And that's why supercomputing and traditional computing is getting specialized using different types of chips architectures. For instance, we have the GPUs, and other things that are being explored, like TPUs, neuromorphic computing, and of course, quantum computers. The second thing is because we need to satisfy the user demands. So one of the main missions of a supercomputing center is to provide the necessary computational capabilities to the users. So if the user demands quantum computers, we need or we have to install or try to install these kind of devices into our infrastructures. And in the end, because we want to adapt to the cutting edge technology and to provide a public service to the community, and especially the research community. And finally, because supercomputing has also applications in quantum computing, and the other way around is the HPC quantum integration and applications that many people are talking about. There are many things where quantum and HPC, of course, can collaborate with, and one of the things is quantum algorithms, of course, but the other thing is also to control the quantum device, you always need a classical computer, and even for calibration and other applications, you will need a classical computer. And maybe HPC, especially with all these machine learning applications that are emerging, it has sense maybe to put them together. So the first thing, of course, I think that we already passed this stage, so everybody agrees that quantum computers are not competing against supercomputers, but they are part of the supercomputers, and that's why we are making this effort to integrate it into our infrastructure, because in the end, a supercomputer are many computers put together and connected to each other, and quantum computers will be just another partition into a big supercomputer, as we have now GPUs, acceleration, and general purpose partitions. And also because a supercomputing center will be a natural place to allocate these devices to offer these services to anybody that is interested in doing research with them. This deployment, of course, it's not trivial because we are talking about devices that are highly experimental still. It's not operational, or at least not as operational as a traditional computer. So in the end, we need several things to be taken into account, because when you arrive to a supercomputing center, you will see a site, so you will not see cables around, or if you see cables, everything will be very smooth and very well placed and so on. And this is important because, for instance, in our center, there is no laboratory close to the supercomputer, so there is no place where you can work on some cabling or some parts of the chip or other things that you may need. So that means that whoever comes to our center, it has to come with something that is operational, that can be plugged, and start working with it. Of course, the reality is more complicated, as you know, but it's something that the vendor or the people that are installing these devices should take into account. So that means that we also need system monitoring, because in the end, we need to ensure the well-functioning of these devices at all times, 24 hours, 7 days per week, because in the end, other people, other researchers rely on our computers to perform their research, their projects, their applications, their calls, and so on. So if for some reason the computer doesn't work, that will affect a whole community. So we are the main responsibles of that. That's why we need ways to ensure this system monitoring and ensure that the device is working properly. Then we also need automatized and efficient calibration, because in the end, the technicians that will take care of the quantum computer are not, or not necessarily experimentalist experts in the main technology, in the same way that the people that take care of the supercomputer doesn't necessarily know how a chip is made or how is the architecture of that chip. So that also means, when I mean about efficient calibration, is we need to know how much time we need to calibrate the device, because that time will not be available for the user, so we need to take into account all these things. And of course, we need a low maintenance technology, so we are not a lab, so we don't want to be replacing parts as many times as possible. It's the other way around. So the point is, we need a technology that is easy or as easy to maintain as possible. That's why, for instance, superconducting circuits, we believe it's one of the technologies that more or less fits this criteria. So our vision is that we are going to the full integration. That means that both the supercomputer and the quantum computer are installed on site. So there is not a quantum computer in the cloud that we are managing or accessing. It's installed in our premises. And for security reasons, this supercomputer is not accessible through the cloud. So you have to connect it directly using a login node once you have this access. And what they share with the supercomputer is the storage at the moment. So we're using Slurm, which is a particular software to control the different queues in supercomputing or in traditional computing. We are using the same for the quantum computing. We are using different lines because in the end, the supercomputer has to pass several tests every day or every few weeks, and the quantum computer has their own. So it was complicated to put things together, and that's why we have federated Slurm. And another important thing here is that the computer is installed Turkey. That means that once everything is installed in our center, the vendor or the provider of the computer has to leave, and all operational has to be managed by the Barcelona Supercomputing Center personnel. This is quite common in all supercomputing centers. Of course, we are doing different exceptions depending on the technology and depending on the center. They may require this close collaboration with the vendor, but this is the goal. The goal is that it will be operational by non-experimentalists. So our quantum computer partition is called Mare Nostrum 5 ONA. Mare Nostrum 5 is our supercomputer. It's one of the main supercomputers in Europe. It's a exascale supercomputer. And at the moment, we have installed a superconducting circuit digital quantum computer. At the moment, we have 5 operational qubits. We are calibrating the 10-qubit chip. And we are expected by the end of the year to have a 35-qubit chip. The technology is provided by Kilimanjaro Quantum Technology and GMV, and on top of that, some of the technology come from Quanware, from Qblocks, and Leiden Cryogenics. And it's thanks to the big project that we have in Spain called Quantum Spain. It's a big effort of 27 Spanish institutions, and it's managed by the Spanish Supercomputing Network. That means that all users in Spain can access to this device through this network. And then we are also installing a superconducting circuit analog quantum computer, a quantum annealer. This is part of the EuroHPC network. So as you may know, EuroHPC is also installing quantum computers in supercomputing centers, and ours is one of those. There are many others. You can find all types of technologies, trap ions, neutral atoms, photonics, recently also spin qubits, superconducting circuits, and this will be available for all European users at the end of this year, beginning next year. This is how it looks like. As I mentioned, there is the shared storage. We have the general purpose partition and the accelerator partition. So this is the pre-exascale classical supercomputer. And then Mare Nostrum Monad, which will have analog and digital quantum devices, both of them superconducting circuit-based. This is how it looks like. So in case you didn't visit Barcelona Supercomputing Center, our computers are in an old chapel, so it's something very nice to visit. This is where the up-to generation of Mare Nostrum 4 was located, but Mare Nostrum 5 didn't fit there anymore, so we have a free space to install quantum devices, which is very nice. We also expect to install the EuroHPC 1 here. And you can see 2 dilution fridges because we are having 2 chips in parallel, so at the moment 5 and 10 qubits. Talking about the quantum HPC integration, it's not like a magic wand that I put quantum and HPC, I connect them, and I have an acceleration. Of course, unfortunately, it doesn't work like that. So that means that we need to think about which applications really require from quantum and HPC. And when I mean HPC, I mean more than 1 core, so more than my laptop, basically. So it's not obvious. Of course, there are many potential applications, and that's the thing that we are working on extensively in supercomputing centers. And from my point of view, I think that quantum HPC integration must be application-driven. That means that once we identify this application, we can work for the integration, not only hardware, but especially the software of that integration. So for me, it's, we need to identify first the needs and then design this integration. Because one of the things that you should take into account, of course, is that the control times are not the same for a quantum computer than a classical computer, and the quantum computer at the moment could be a very big bottleneck. Depending on the execution times and the initialization times and how much time it takes to translate from quantum circuits to electronics and so on, that could possess a huge bottleneck because we are competing or we are waiting for these HPC nodes, which are many, many thousands of nodes that can be very fast. And all the software here is really optimized. So if we have to wait until all of this cycle arrives here, so it could be a bottleneck. That's why we need to design a proper scheduler to orchestrate all these hybrid applications that take into account that we have thousands of HPC nodes and others more than 1 sometimes quantum nodes. For that, we identify one application of quantum HPC, and especially it helps us as a testbed to design a library that is hybrid, which is the quantum circuit cutting. So as you may know, there is these algorithms called quantum circuit cutting that given a big quantum circuit, you can cut it, and you can distribute it into different quantum processing units or even simulate these different parts. Of course, that comes to an exponential cost. Each cut that you do, it will generate an exponentially growing number of subcircuits, but it's a way that we can execute, not only in the present, but also in the future, very big quantum circuits in different processing units that are not big enough to execute the full circuit. So this is well known by the community. So we use this application to test and to design a full library that takes into account all this distribution of these subcircuits between quantum processing units different or even with the simulation in GPUs or in CPUs. So we designed what is called QD-SLEEP, so you can check the documentation here, and it's built on top of COM Superscalar, which is a task-based programming model that has been developed at the BSc from the last 10 years. It's used in AI, it's used in supercomputing applications, in many things. So the main idea of QD-SLEEP is that given a big quantum circuit, it can split it into small subcircuits depending on the user demands. Like I have a 5-qubit chip maximum, so I cannot split the circuit in subcircuits that are bigger than 5 qubits, otherwise I couldn't I will not be able to execute it. So things like that. So this is designed by the user. But all the task management, so each execution of a circuit, each repetition will be a task that will be executed in one node. That node could be a quantum processing unit or could be a standard classical node because we are simulating this part. So that will depend on the user needs. So that was a very big test bed for us to execute this hybrid application. So what happens is we translate the quantum circuit into an acyclic graph. We use also supercomputing and graph partitioning algorithms to find the optimal cuts. Again, this is exponential, so having the optimal cut is not trivial. And then we decide if we want to execute it in QPUs, in GPUs, or in CPUs. So let me show you some of the results. If you check the preprint, you will see many other benchmarks, but I just choose these two. The first one is we use the hardware-efficient ansatz to benchmark the simulation in only CPUs. We also did the same with GPUs. And the point here that I want to show is that as we increase the nodes, so this is classical simulation, so as we increase the nodes, we see this exponential decreasing in the execution time. This is something that is telling us that we are parallelizing things properly. If we don't have this behavior, that means that the parallelization of all these tasks is not well done. So we have something that is highly parallelizable. Also, something that I want to say is that the simulation algorithm is just wave function exact simulation, so we don't use even tensor networks and MPS. That could be reduce the execution time, but what we wanted to prove here is just that we can reduce this exponentially. And then the other thing that we want to show is that we design a full fine-cut algorithm to decide where are the optimal cuts. And this is, and we compare it with the IBM CKT algorithm, which is the library that IBM has to exactly decide these things. And we obtain better number of cuts, and also execution time is reduced. This is because we are also parallelizing this part. So we are parallelizing absolutely everything that is possible in these applications. And this table also summarizes some hybrid executions. So as you can see, we try this in CPU cores, in GPU cores, in our quantum processing units, so the Mare Nostrum Ona, and also we use the cloud, the IBM cloud, and with the IBM Q Marrakesh, which is a more than 100 qubit quantum device. And of course, the executions on local QPU are faster than using the cloud, as you can expect, because in the end, you need to connect to the cloud, and that takes time. So the executions on site are faster. And then also, of course, using the QPU only is faster for larger sequence than performing small ones, as you should expect, of course. In the end, that's why we need a quantum computer after all. But our goal here was to just benchmark that our library was working properly with different types of executions. So then let me move to the next part, which is the benchmarking quantum computers. So first of all, what would you like to benchmark? So in classical HPC, we have the benchmark, which is the LIMPAC. So basically, diagonalizing a huge matrix. In quantum computer, we don't have that. So we are still discussing what are the best benchmarks to check what is the performance of a quantum computer. And from my point of view, we have different things that you can think of. Of course, the deployment means how calibration runtimes, how long it takes to calibrate the device, how many times you have to calibrate the device, how is the circuit compilation or transpilation, that's part of the software of the quantum computer, and so on. Then you can think about the integration, where I think that hybrid workflows, as the ones that I show, could be a good benchmark to just run it and see how long it takes. Then we have non-trivial but easily classically certifiable tests, like factoring a number, for instance, or integrable spin model simulation that we know how to solve it classically, so we can check if the result is good or not. But then there is another subgroup of applications, which is the quantumness. So checking that the quantum computer is actually quantum, and for that we have the Bell inequalities, non-locality tests, and also the generation and certification of highly entangled states. So in the end, I will focus on that, the final one, because in the end, quantum computers must be able to generate and hold highly entangled states. Otherwise, we are losing the potential quantum advantage. So for all types of quantum of entangled states, there are many types of classes, and as you grow in number of parties, and if you grow the number of dimensions, things become very cumbersome, and it's very difficult to certify and also to define what does it mean to have a multipartite entangled states. But one of the main entangled states are called absolutely maximally entangled states. These are pure states whose all bipartitions are maximally mixed. So if you take the two parties, these are the Bell states. If you take three parties, these are the GAZ states and its generalizations, but as you grow the number of parties and dimension, it becomes very, very cumbersome to find if an AM state even exists. So it happens that for some number of dimensions, AM state doesn't exist at all. And that's the case for qubits. 4 qubits and more than 6 qubits, it doesn't exist at all. But if you grow the number of dimensions, you will find eventually an AM state. And some of these AM states can be generated from graph states. That means that it's very simple to generate these states and also to construct them. But for some reason that we don't know why, some of them are are not possible even to have a graph state, but an AM state exists. These are the non-stabilizer, let's say, AM states. So these AM states have applications in quantum error correction, some of them, also in multipartite quantum teleportation and other applications that people are studying. And one of those is, of course, benchmarking quantum computers and high-dimensional quantum computers. So AM states are easy to generate in a quantum computer if there is a graph state that exists, because you take the graph, you translate it into a circuit. So basically, every node corresponds to a Hadamard gate if you start with the 0 state, so it's a plus state. And every edge is a control Z gate. So that's very simple to construct. And that's why it's for qubits, you have for 5, 6, and that's it, because there are no more AM states. Then there are certain forms of AM states, for instance, the AM of 4 qubits that has this particular form, where you can find a circuit that is easily to program, which is this case. You need the Fourier gate and the generalized control node gate, or the other gate. And then you can even take AM states of higher dimensions and try to simulate it with qubits, for instance, making this mapping. And this is an example of a Q3 control Z gate with 4 qubits, so you can play with that and you can generate that. Shouldn't be super difficult. The point is if there is a graph state, of course, because if there is no graph state, you have the problem of, okay, how can I construct the AM state in the first place, even in higher dimensions? So that's the thing that we explored recently. So there are some states, AM states that doesn't have a graph state, but they can be generated and they exist. And these are the non-stabilizer, we call them the non-stabilizer AM states. And the point is that why do you want to do that if you have the graph state equivalent? Well, in some cases you don't have it. And even if you have it for benchmarking purposes, it could be interesting to have these more sophisticated circuits that require more sophisticated gates, and in the end generate a highly entangled state. So we thought that for benchmarking, there could be interesting, especially for high-dimensional quantum computers. So we proposed some explicit circuits to generate these states based on some recent works on the search of these AM states. And finally, let me finish with these applications of high-dimensional gates and also the cloud computing application, which in this case was cloud, but in the future I hope that centers like ours can provide also this kind of services, because, for instance, we are also enabling pulse control in the near future. Let me explain that for non-locality tests, so to prove quantumness, there are two main ways. The one thing is the Bell inequalities and many families of Bell inequalities. The other thing are the GAZ-like test. So basically, the two reasons why we have Nobel Prizes on that. So for qubits, it was proposed by Greenberg, Hoare, and Zeilinger, the theory in the 90s, and then we have the experiments by Zeilinger and also Aspect and so on that prove this GAZ state entanglement. But then the generalization to higher dimensions, surprisingly, it took a lot of years. In 2014 or so, with the works of Lawrence, they proved how to generalize the GAZ state test to higher dimensions than 2. And the experiment has not been performed yet. So we didn't prove quantum non-locality in that regard of without inequalities, let's say, with a dimension greater than 2 and more than 2 parties. So for that, we need to generate the high-dimensional GAZ states. And that has been done with photons, but it took a lot of time to generate them. So it was not feasible to propose even the non-locality test after the generation of the GAZ state. And that's why we thought, OK, why about using superconducting circuits? They are much faster. They are programmable devices. So maybe we can do this type of test. So we did that 3 years ago, and we did that in the cloud using one of the IBM devices and using the pulse level control. So we had to calibrate all these gates and so on in the higher dimensional subspace, in the 1-2 subspace. And we certified tripartite three-dimensional entanglement, both with raw data and also with mitigated data. Mitigated, I mean mitigated with the spam errors. And the good thing here is that it took only 1 minute. And it was 30,000 times faster than the photonic experiment. Therefore, it enables to test this non-locality after that. The problem that we had is like all of us were theoreticians, and we didn't know how to really check these things. So basically, we had relative phases in when we applied the gates in the 0-1 subspace and the 1-2 subspace. So the way to mitigate that was to scan until we were able to cancel the phase. But that was not something feasible if you want to perform a non-locality test after that. And actually, the experiment is very simple. So if you are interested, let me know, because I have everything programmed and prepared, and just need an experimentalist to run the thing for me. So yeah, that's why I wanted to present this in this audience. So I'm trying to find someone that is interested on that. But in the end, a good thing of here is that we were able to do high-dimensional experiments in a programmable device, we as a theoretician, so we didn't, I mean, it will be much greater results, of course, if we have some experimentalists around, but the point is we did everything in the cloud. And I think that's the goal of centers like ours that work in supercomputing, that to enable this type of applications as IBM has been done recently. So with that, let me just conclude with some messages. First of all, supercomputing centers are making this effort to install quantum computers in their sites. This is not trivial because we don't have a lab, we don't have experimentalists, so that means that everybody has to work together to make it possible. Also, we need these hybrid workflows to orchestrate all these applications and hybrid applications in quantum and HPC. And that's the thing that we are working on extensively, all these software lines that will hide many things and many tasks to the users that are not expert in HPC, for instance. And that's why we propose the QD sleep that you can check. And also the generation of highly entangled states, we believe it's a good benchmark. It's one of the benchmarks that should be included somehow in all these benchmarking suits for quantum computers. And finally, I would like to stress to the community that we need to make an effort to really think which applications really require quantum and HPC, because that's the main reason why centers like ours, why EURHPC and many people are making the effort to install these quantum computers, to also integrate them with the supercomputers. I think there are many things that we can try, and that's why these two communities are coming together. So that's it. Thank you very much for your attention, and happy to answer any question.
Great. Thank you very much, Alba. Do we have any questions from the audience or anything? Yeah. All right. Let's see how my arm is. Oh. Oh.
Oh, it's not working.
Did I break it?
Oh, now it works.
Yell. Yes.
Yes, yes, I can hear you. Mm-hmm.
So could you maybe comment more on that? Why have you chosen to work with quantum circuit cutting frameworks and shown that on HPC? Is there some reason you picked this?
So we picked quantum circuit cutting because to me it was the simple example that I can explain to people that doesn't know what a quantum computer is at all, to try to find an application that has sense also for HPC. So they are used to work with these workflows. So okay, let's try to find an hybrid workflow. Okay, we don't have a specific application for this hybrid workflow, or if we have it, it will be very cumbersome, the application itself. So let's try to find something simple, but at the same time has a lot of applications, which is meaning how are we partitioning these circuits and how are we executing that. And of course, in the long run, you are not using classical simulation after all, so all these CPUs, GPUs can be removed. But in the short term even, and maybe even in the long run, we are using exact wave function simulation. But if we include tensor networks here, we, by the way, have also used COM, so we are planning to upgrade that in that direction. That means that this could even be used for quantum simulation, for classical quantum simulation. But our goal, at least my particular goal, was to provide a test bed so we can extend this workflow called COMS to also include quantum nodes. So all this group of people and all this community started to be more familiar of how a quantum computer works, what are the response times of the quantum computer, and so on. So something that we didn't try and not even analyze is the results of this execution. So of course, we didn't expect to reconstruct the expectation values and so on. That's the next thing that we are now working on. But I think that, that's a very good test bed to start working on and have it something that is working, let's say.
we have any? Oh, we have another question over there.
Good catch.
Thank you for a nice talk. I was wondering if you had already some ideas about how you would integrate these HPC components with error correction, which is already going to involve lots of hybrid classical quantum processing. So do you imagine decoding tasks being dispatched in such a way? Have you started?
Yeah. Definitely, and that's why another reason why we use COMS. COMS is a task manager that is being used in traditional machine learning. So something that I will be very happy to explore in the next months. It's okay. Let's try to program some kind of quantum error correction with that. I'm not sure if our quantum computer can manage that at the moment. But yeah, definitely quantum error correction is one of the applications where I think that HPC will play an important role. And not even quantum error correction, even just the storage and reconstruction of probability distributions of all your qubits, because for 5 qubits it's very easy, but if we want to scale to 100, 1,000, and so on, only managing all these bit strings will become cumbersome. So I think that all this resource allocation, data storage, and so on that is used in HPC will be reused here in quantum computing.
Okay. Yeah, we have a question up here first, just to spread it around, and then we'll come back.
I'll do a second step, I guess.
Thank
This
you.
is funny.
You showed this nice figure where you had like the circuit which was directly pointing to the QPU. And I was wondering, like, what is the interface there? So how does the circuit being transmitted to the QPU? Like, do you use CASM or something like that?
Oh, okay. Yeah.
And then I was also wondering, like, I guess some of the QPUs need very different, like, hardware-specific compilation. And so how does the user sort of get informed about the hardware specifics? Like, is there some device model which kind of goes all the way up to the stack? And yeah.
Yeah, this is a very abstract figure because in the end our QPUs are all superconducting circuits. Actually, it's one superconducting circuits at the moment. It's digital. Well, it's double the system, so we have two. So we don't have to worry at the moment of different technologies and different response times, but I include here, okay, it could be different for each QPU. This control electronics, at least. So this step here. So yeah, in general, what we do, at least what we are doing at the moment, is all the information about the recently calibrated device and so on is in our web page. So you can check if you are one of the users, you can enter to the portal and you can see everything. But one of the things that we are working on is precisely on all this benchmarking that I didn't talk about, but the one that this part here, to also provide this kind of information to the user so they know how much time they will take to execute everything. And even if it's not for the users, for us it will be very relevant. And that's why these big projects in Europe, the Euro HPC ones, are so important because each of us are targeting different applications, different technologies. All of us are integrating these technologies with their supercomputer, which in the end, the supercomputing part could be very similar to each other. So that's the thing that we are working on right now, to exchange our experiences and seeing, okay, how difficult it is to integrate all of that. But answering the first part, yes, it's OpenQuasm is the last thing. So what we use at the moment is Kibo, which is an open source language. But in the very end, Kibo translates to OpenQuasm, so you can also send circuits in OpenQuasm.
I think we had one question over here first. Okay, we have one more question back here on the stairs. Oh, don't get hit. Oh.
Thank you. Very interesting talk, many thanks. I've been in a couple of sessions or events where this HPC and quantum computing has been discussed. And a little question that I have on this context is, for example, 5 years from now, as you know, the HPC is dealing usually with very large workloads where I/O could be one of the aspects to consider, but also what you mentioned as well, intrinsically the storage or the access to the data and so. And if we see some of the use cases considered right now with, I don't know, with chemistry or quantum machine even, quantum machine learning. So my question to you is how you visualize the added value of quantum memory in this hybrid context.
In quantum memory?
Yeah, in 5 years from now.
But we don't have quantum memories
yet.
So that, yeah, I mean, depending on the application, you will require memories or not. So for simulation in general, you can go without it. For quantum machine learning, I think in the long run will require the quantum memories, but we don't have that yet experimentally. I'm not sure if I understood your question.
Right, but for example, if we see the HPCs, right? So the HPCs are having a lot of databases, and that's a critical element. So I was wondering whether the quantum memories eventually could, instead of having some interaction from quantum, the quantum computing towards the HPC to have the entire workloads quasi within the
So you mean storing data in quantum memories, like classical data?
In order to do the quantum processing.
Okay. I'm not sure, to be honest, because in the end, this, as far as I know, this doesn't exist yet as an application. Is anyone working on quantum memories to store classical data, or, I'm not sure if I can provide any idea on that regard. So my point of view, talking in general of how quantum can help HPC, is that many applications, of course, that we are using HPC at the moment, like simulation chemistry and so on, could be at least one part of the algorithm be running quantum, and that means reducing the energy demands. So that's the other thing. So another good thing of having this installed in our center is that we are now measuring the exact energy that is required to run everything. So we talk about this potential quantum advantage of quantum, it will be more energy efficient, blah, 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 but the real thing, we'll see. So that's why we are now using the same measures to measure our supercomputer and the quantum computer, both together and separately. So we will provide real figures of how, if we need to even optimize processes, so because theoretical is one thing, but experimental is another thing. So
thank you.
Thank you.
Okay, maybe we have time for one last question, if anybody has anything. Okay, maybe I can ask one really quick question. Since this is a very interesting topic that you just brought up about the energy cost associated with running a quantum computer, do you have anything preliminary that you could say about how much it takes? Is it just cooling down the fridge, or?
Fortunately not. I mean, we know how much it takes, but not personally me. So you know better than me probably. I mean, it takes, of course, it takes 1 day as on all these fridges, and I think it's kilowatts or so, but I'm not sure. So I'm not the experimental part that take care of that, fortunately for them. But yeah, our plan is now, we are working on that direction. We have some particular software features that we use in HPC that we are now installing in our control electronics, or we are planning to installing in our control electronics, so we can check really how much energy is expended in the device, plus all the requirements from dilution fridges and so on. So we are now working on it. This is the thing that I can say.
Okay. If there's no more questions, let's give Alba a hand once again. Thank you very much. And our next speaker today is Philip Allman from Parity QC, where he has a talk entitled Scaling Enhancements of Quantum Algorithms on Superconducting Qubit Hardware. Please, Philip.
All right, thank you very much. So in today's talk, I want to tackle the problem of qubit connectivity. So as you all know, most of the QPUs with superconducting qubits have limited qubit connectivity. They are arranged in heavy hexagonal structures, square lattices, or something in between. And many of the quantum algorithms actually require high algorithmic connectivity. And two examples of this would be, for example, the quantum Fourier transformation or the QAOA. Depending on the problem, you will also have an all-to-all connected algorithmic problem, which you then somehow have to map to this sparsely connected QPU. And an intermediate solution of this would be to insert swap gates. So for the QFT, there's, for example, an implementation by Fowler et al., which maps this to a linear chain using swaps. And there are other swap network strategies to tackle this for the QAOA and alternatives. So today I want to present an efficient solution which we call the parity twine. And this is a swapless implementation of quantum circuits. And it's not limited to the QAOA and QFT, but we have benchmarked it against these two algorithms. And there we could see that we are outperforming state-of-the-art alternatives for these two algorithms. And this should improve the circuit implementation of important cornerstone algorithms on multiple qubit connectivities. So what you can see here on the top right graph is the average gate count we need for the quantum Fourier transformation as a function of the inverse qubit connectivity. That means like the linear nearest neighbor, that's the linear chain of qubits, would be sort of the least connected system. And even there, we could see an improvement of our methods in comparison to the best known alternative. And then this goes down, and we could prove optimality for an all-to-all connected system. So to understand a little bit how we did this, I have to go one step back and explain a little bit how we came up with this algorithm. And this is done by a method which we call the flow formalism. And the foundation of the flow formalism, the parity flow formalism, is a very simple observation. It says that the C0 circuit maps set eigenstates to set eigenstates. And then you can actually track the C0 circuits by their effect on set eigenstates. So if you think about it, you have two qubits. You can assign these qubits with labels. And then the effect of a C0 would be to write the parity of the one qubit on the other and leave the other one as it is. And if you write down the quantum state, it would look like this. And this is the associated truth table. So this, of course, also doesn't just work for the eigenstates, but also for the superposition of those. So it's a very general framework. All right, and now you can ask the question, okay, given the problem that I want to implement all two-body interactions between a certain amount of qubits, how do I do that? And the first step you could do is to say, okay, how do I encode all two-body interactions, all two-body labels that contain the label of the first qubit, L1? And a building block we use for this is that one. So if you combine a C0 with a swap gate, two C0s cancel, and you effectively get a double C0. And the effect of this double C0 is that you move one label to the other qubit, and you create a parity on the other qubit. So you have like the pair interaction now at this qubit, and the other one moved up there. So now if you do this with a linear sequence of these double C0s, you can see you actually create very efficiently all combinations of these two-body labels containing L1. And if you would now have an iSwap natively, this would make sort of the optimal implementation of such a parity twine chain. But of course, you can also decompose it into C0 type gates. So now, to create all, not just the one which contains L1, but all combinations of labels, you would kind of stack these twine chains along each other, and with that you can create all of the two-body interactions. And if you would track the labels during that circuit, it would look like that. And then with a final stage, you would kind of return to the single qubit labels at the end. And if you look at this, and if you're familiar with our parity architecture, this is actually the parity architecture, but in time. So before, we always looked at this in a spatial way, where we would have all two-body interactions at the same time, but now we have them in a time-wise manner. And to do algorithm with that now, you would sort of insert single qubit rotations at the positions where you have these two-body labels. And this effectively maps back to a logical multi-body operation by doing just a single qubit operation. And in the case of the QFT, it looks like this. And if you now count the two-qubit gates and the depth of the two-qubit gates, and you compare it to the best known alternatives, we see an improvement in both figures of merit. So we went one step further and actually also tried to experimentally validate this improvement and run some experiments on the IBM Heron chip R3 very recently, and did this QFT experiments up to a system size of 50 qubits. And there you can see by the slope of the process fidelity of the QFT, that we could gain a great advantage over the best known alternative approach. So now the question is, so this was all now a linear chain. So what we did here, we basically put a linear chain through the heavy hexagonal structure of the IBM processor. And now a question is, can we sort of use this extra connectivity the processor gives us to make it even more efficient? And the answer is yes. And here we kind of distinguish two things. So we call sort of this chain of DC nodes the backbone of the algorithm. And then to this backbone, we can add legs with single C nodes to create these extra labels to sort of make use of this extra connectivity. So what we can do, we could put this red backbone through the heavy hex and add legs at the sides to create all the labels we need. So on a heavy hex, the QFT circuit or the general parity network would look like this. And if you now look at the gate count and the depth again, we could improve the gate count by a factor, but we sacrifice a little bit in the depth, but the depth is linear and the gate count is quadratic with the system size. So we also try to validate this experimentally. So we got this red line on top of our experiments, and we could show only a very marginal improvement of our results. And we think this is due basically to this fact that we have increased the depth a little bit, but the experiments are not optimized yet to really show the full advantage. But now IBM is kind of turning towards the square grid. It's the Nighthawk is announced for this year, and many other companies like IQM, Quantware, etc. do have square grid devices. So of course we also asked the question, can we do something on the square grid which is maybe even more effective? And the answer is yes. We can sort of use our backbone leg structure again on the square grid. And now for every backbone node, we have two legs which generate the parities outside of these legs. And we can kind of propagate with this fishbone structure through the square grid to create our parity network. And if you now look at the scaling, we again could improve the two-qubit count and increase the depth slightly. So now the question was, can we even improve the square grid apart from this strategy? And the answer is again yes. So if we would have a ladder structure, and I mean a ladder is part of a square grid, you can actually run two backbones in parallel. And this would make such a parity network. And if you compress this, you can make actually a very, very dense circuit. And the results of counting the gates are given here. So we again improved in the gate count of the two-qubit gates, and we could also improve the depth with the ladder. Okay, so now we also wanted to verify this experimentally. So we went to do experiments on the IQM Garnet machine in this case, to have a square grid device, and did basically the same experiments for the QFT as I've shown before for the IBM machine. And we could verify that the twine ladder approach is by a big margin, and this is a log plot, or the plots before were log scale, by several orders of magnitude, improves over the best known alternative implementation for QFT. So I want to stress that this is not limited to QFT. So QFT was sort of the first thing we looked at, but our circuit implementation approach, parity twine, actually is very general. So there are other applications which go beyond that, and one example is QAOA. And due to this nice triangular structure of the parity twine algorithm, you can actually stack several triangles on top of each other for the different QAOA rounds and make a very compact circuit out of it. And if we now would, for example, compare again the best sort of known linear alternative for QAOA with our twine network, we again see an improvement in 2-qubit gate count. And depending on P, but the advantage is relatively fast if you increase P, also an improvement in the depth. And there was a previous conjecture by this paper from IBM Zurich that the best you can do is basically a linear swap network, which you put on a square grid device or a higher connected device. And we could actually prove here that this conjecture is wrong and that you can actually make use of this extra connectivity by using this parity twine method and improving the gate count and the depth even more compared to the linear approach. All right, this already brings me to the conclusion. So I've presented a swapless implementation of quantum circuits. We have seen for several qubit connectivities that we can improve over other known algorithms. And this is a general approach, but we demonstrated it for QAOA and QFT to show the advantage. Thank you. And this was the work of this great team at Parity-QC.
Great, thank you very much, Philip. Do we have any questions in the audience? Anything? Oh, Runa.
Thank you for a very great talk. You say that the parity twine is general in the sense that you can pick anything and then you do a parity twine optimization over this, or that's at least what I'm hearing. And it makes a lot of sense that you give me a QFT or a QOA, then you can, for these two specific circuits, try to optimize. Do you have some kind of intuition about what the workflow would be for a general circuit? I give you a circuit, how would you parity twine optimize this?
Yeah, so this is actually described in this paper here, where we describe our very general parity flow formalism. By the way, the first author, Baron Glover, I think he did he studied here in Delft. So the idea is always basically this, that you kind of track the labels through the circuit. And I said that it's a very general approach, but it's maybe not always the optimal approach, because this works very well if you are in a single basis. That means, like for the QFT or for QAOA, you always have to implement ZZ type of interactions. So you stay in the Z basis, and this works well. You could do something very similar for the X basis if you just put Hadamard in front of everything, and then it works the same way in the X basis. But if you have mixtures, for example, if you want to implement the Heisenberg-Hamiltonian for some quantum simulation, you would have X, X, Y, Y, ZZ terms. And there, the formalism might be not the optimal approach, because you have to always sort of make a block encoding for one direction, and then another one for the other basis, and you would have to make sequences of this, and this might not give you the optimal approach. So this works very well for circuits that basically stay in a single basis, if that makes sense. And it is general, but it's maybe not always the best. And we are trying to figure out how exactly to define the class of circuits where it gives you an advantage. QFT and QAOA were very obvious for us because we knew that we can find an advantage there, but it's still an open question how big the advantage is for general circuits.
Thank you.
Okay, I think we have time for one more question. Yeah, just over here. Oh.
Thank you. I was wondering, maybe I missed it, but did you talk about the approximate QFT? Like, did you consider that as well? Because given that for 50 qubits, your fidelity is like 1%, which is not surprising. I'm just wondering, probably the approximation error would be negligible comparatively, and you may get better fidelities.
Yes, so we have an ongoing project on that to extend it further for the AQFT. And I think we don't have numbers which are sort of published yet, so maybe we have to wait a little bit. But yeah, we're working on this, and the AQFT is for sure the future, at least in the near term. And since you asked the question, I talked here about the best alternative approaches, and this did not include dynamic circuits. So here in this comparison, I didn't include measurements, mid-circuit measurements in classical control, just because we want to compare it to the most comparable algorithm. And for the mid-circuit measurements, you either have to sort of destroy your quantum state, or you need an ancilla or ancillas. And this would have been a nice comparison. So we took the best non-mid-circuit measurement type of circuit as a comparison.
Makes
just
sense,
to be fair, yeah.
Thanks.
Great. Thank you very much, Philip. Let's give him a hand once again.
Thank you.
Our next speaker now is Francesco Monzani from University of Milan. He'll be talking to us today about universal gate-based quantum reservoir computing for sequential data processes. Please, let us give him a hand.
Thank you. Okay, so does it work? Yeah, okay. So before I start, let me thank also my collaborators, Emanuele Ricci, and Luca Nigro, and Enrico Pratti, who is my PI, and the PI of the project. And so today I'm going to talk about reservoir computing, and of course, quantum reservoir computing. And let me explain just in a nutshell what reservoir computing is. So essentially, it is an unconventional machine learning paradigm in which essentially you deal with time series, so sequential data, so data that can be represented by some sequences. So these are some numbers from 0 to 1 or some normalized numbers. And in reservoir computing, you deal with a recurrent network because essentially you need some memory of the past. But the peculiarity of reservoir computing is that you don't want to train the network, so you don't want to adjust the parameters inside the network, but you just want to train a final layer, so a readout layer. And so, of course, the very simple reason to explain why we do reservoir computing is because training is very easy. And this is very, very important in quantum machine learning because you have many issues when you do the training of a quantum neural network. So, for example, in quantum reservoir computing, you don't have baryon plateaus, you don't have any problems. And moreover, let me mention also that if you look here in Google Scholar, let's say you write down reservoir computing, you will find many implementation like very different physical reservoirs. So you can replace your network with essentially any physical system you want, depending on the type of data and, of course, the system you have at your disposal. And, of course, quantum reservoir computing is reservoir computing when the fixed network is a quantum system. Also, let me mention that it's very versatile. We will see a couple of examples, but believe me, it's very versatile architecture. Okay, so today in particular, I will deal with which is called gate-based equal-state network, which essentially means that we will use a quantum circuit as our reservoir. So we have our time series, U0, U1, UL. We inject the data inside the state of a quantum circuit with a unitary operation. So this must be parametrical, because we need to encode a number, so we essentially use rotations, nothing more. And then we do mid-circuit measurements. So, of course, we need an hardware that can do mid-circuit measurements along the circuit execution. And we repeat the operation. We construct a readout matrix with some observables. For example, Pauli observables are fine. And then we do essentially linear regression to construct a function of the inputs. And so this is a supervised machine learning technique. So essentially, we select a subset of targets as a training set, and then just the simple, straightforward stuff when you do machine learning, supervised machine learning. So let me stress again that we need mid-circuit measurements, of course. Otherwise, you must think another architecture, and this is straightforward. We have sequential information in entrance, and we need some sequential decoding. And immediately you realize that this cannot work as it is, because essentially when you have a quantum system, any quantum system, and you do measurements, repeated measurement of it, you lose coherence. And this means that if you represent your state as a 1-qubit state on the block sphere, the state is going towards the maximal to the identity, so the maximal mixed state. And where you are in the identity, you cannot do any input encoding, because that's a very trivial equation. Any unitary in the identity is again the identity, so no input encoding is possible. And so you need a mechanism to restore, at least partially, the 0 state. So the evolution is going towards the maximal mixed state, and you need some kind of mechanism, some kind of damping, in order to restore the 0 state. Because, of course, we are measuring along the z-axis, and so you need some mechanism that goes towards the 0 state. And this is just quantifying this idea. So the more I am far from the identity, the better I can recognize inputs. So this is the states after the input encoding. This is the distance between them. And on average, I mean, the farther I am, the better I can recognize inputs. And this is, I mean, the first starting point to have a meaningful algorithm is that you can recognize different inputs. So here you see, if you're in the identity, there is no way you can recognize X and Y, even if they are different. And we use trace distance because we have some theoretical background where you can use any kind of distance between density matrices. And yeah, so the first idea we come up with, is can we use the noise inside a quantum computer in order to ensure the damping? Because, okay, we know that quantum computers have many sources of noise, and in particular, we have amplitude damping inside a quantum computer, and even inside a superconducting quantum computer. So the question is, can we exploit the amplitude damping inside the quantum hardware to achieve this damping? And the answer will be yes. I will show some results later on. But of course, this is not satisfactory because you cannot, in a quantum computer, it's very difficult to tune the parameter that regulates the damping. Of course, you can do something, but I mean, you cannot think about, I mean, you can increase the amplitude damping, of course, but I mean, if you increase the amplitude damping, maybe other sorts of noises are increased, and so there may be issues. And so we developed a second algorithm in which essentially we can simulate damping towards some ancilla. So this is the qubits used as the reservoir in the line above. And then we use some qubits as ancilla, and with these simple ansatz, we can restore partially the 0 state of the state of the reservoir. And let me stress that we don't do resets of the qubits after measurements, so we have some memory of the incoming inputs, but we need reset of the ancillas, because I mean this is required by the ansatz. So in the second implementation, we need both mid-circuit measurements and reset. So this can be hard to implement on a real quantum computer, but still, this is what it is. I mean, this is our algorithm. And I just for the results, let me stress that I will call lambda the parameter that quantify the amplitude damp and the noise in the system, and with theta the parameter that we can control to ensure the damping, just symbols. And this is the ref for the works. And first of all, here you see a very simple simulation in which we inject a random input inside the reservoir. We do measurements, we do repeated measurements, and we keep on with the evolution. And you see, if you don't have any noise, any source of damping, you go towards the identity. So this is the distance between the state of the reservoir and the identity. And you see, if there is no noise, you go towards the identity, and then you cannot do any input encoding, and so you cannot do any computation. While if you add some noise in the simulation, some amplitude damping or some controlled damping, you reach a sort of plateau, which is far away from the identity. And you see this does not, I mean, this depends on the number of qubits, but you are not, I mean, you are not hindered by the number of qubits. So you don't have some course of dimensionality or whatever. The mechanism is stable if you increase the number of qubits. OK, so we have some hope that our algorithm can work. And so first of all, let me just present some very common benchmark in the reservoir computing. So the first one is just linear memory. We require the system to give back the input some step before. And this is a very, very common functional for benchmarking quantum reservoir computing. And this is called NARMA. It's just a nonlinear functional that depends on the past. Sorry, it is YE missing, sorry. And then also you can use a reservoir computing for forecasting task. So we use it to predict the next step solution of a chaotic differential equation. And OK. And first of all, the simulation with noise. So we add the simulated noise to the execution. And in the blue line, you see the error and the memory. Sorry, the blue line is for amplitude damping. And you see immediately, if you switch on amplitude damping, the blue line, immediately the error drops almost to 0. And the memory goes near to 1. 1 is the maximum. Of course, you don't reach 1, but almost. And otherwise, if you had a phase damping or depolarizing, OK, you can simulate very easily with Qiskit. It's just remain the same, so you don't gain anything by adding other source of noise. And in the line below, you see just one experiment. So this is NARMA 8, so 8 steps in the past are required to reconstruct the function. And you see this is the test part. And this is the training part. And you see, in the noiseless execution, essentially you don't have anything. This is just an oscillation around a mean value. But if you switch on some amplitude damping, you see the reservoir computing is capable to do some reconstruction. And this is for simulated noise. Sorry, this is for simulated noise. So we try to simulate the real noise in a quantum computer, while this is the results for the second type of algorithm, so the one with the controlled damping. So we can now we can control from, I mean, by hand the parameter for the damping, and you see immediately again if you switch on the damping. So if you increase the damping, you reach good memory here and very low error, and you see the memory is for at least 15 steps, so not bad. Right? Not fantastic, but I mean, and this is stable till the 10th step. And this is again for the forecasting task. So you have chaotic dynamics, and again the reservoir computing is capable to reconstruct the dynamics and also to predict the next step if you add some damping. And you may ask, OK, what about a quantum computer? So in the line above, you see the experiment just relying on the QPU noise. This is the noise from IBM Torino. So the fact is, this is not enough noisy. I mean, everybody says, oh, we need less noise. No. Sometimes you need much more noise. So here you don't have enough amplitude damping. And you see, again, this is just, I mean, you are just hanging around a constant value. But if you induce some damping with our algorithm, so towards an ancilla, you see that something works. I mean, of course, you have much less memory. This is the memory capacity. It was 15 on the simulator. Here is just 5 or 6 steps, not much more, but still something. And you see also the reconstruction of the normal task is quite satisfactory, at least until, I say, 5 steps back in the past, or 6, something like that. Here, maybe you lack some memory, but still, I mean, it's far better than this one. And OK, before I conclude, let me also mention very briefly that we have some theoretical results that serve as a background. So in particular, we can prove that our architecture is universal. Universal means essentially that you can represent with any wanted solution any given functional. So this is very theoretical, very fundamental. So I don't want to enter into the details, but just to say that we have some theoretical results that support our empirical results. So, I mean, this is interesting for me. And yeah, so yeah, essentially you can prove that if you have an evolution with contractive and non-unital noise, then you have in fact a universality, and without this you don't have it. So again, you have some theoretical baseline, and yeah. OK, so that's all. Just some conclusions for you and some advertisement for me. Thank you. And if you have any question, please.
Great. Thank you very much, Francesco. I think we might have time for one very quick question. If there's anybody out there. Oh, yeah. Sorry, I think we have the cube over here. Yeah, very quick.
Thank you for a great talk. OK, so can you give me us a little bit of intuition about why you chose your theta to not be just 1? It looks like you're trying to do a partial reset of your qubit. Can you give us, you show here that your universality given a non-unitality transformation. This seems very non-unital. It's cool. It's like implemented dampening, but why not just set the dampening for a full reset? Does my question make sense?
Yeah, because you need some memory. If you do a hard reset to the 0, you completely lose the memory of the past inputs. So you need some balance between, OK, ideally you want to be in 0 when you do input encoding, but you want also some memory, and so you have some trade-off. If you ask me which is the optimal trade-off, really, I don't know. We just try to, balance the things, but yeah, this is the reason, because you need some memory of the past. There are implementations also, let me mention also this, in which you do hard reset of the reservoir, but then you need some ancillas to have the memory of the previous state. So maybe this is more common, but yeah, you need more qubits, and so it's kind of, here you can have full reset here, but then you will need some ancilla reservoir for the memory. Yeah.
Thank you.
Great. Help me in thanking Francesco again for his great talk. This is for you. Thank you. Next up, we have Klaus Lagener from the Walter Meisner Institute. And today he's going to be talking about simulating gauge-invariant SU2 Yang-Mills theory with near-term quantum computers. Give it up for Klaus.
Thank you. And thank you for staying around despite the weird title. Don't worry, I spent a minute to motivate Yang-Mills theories to you. We believe it's a bit of a niche field, but might have some scaling prospect, especially for near-term devices with variation methods. To set the stage, high-energy physics contemporary is struggling, like me. With scalable, fast, and accurate simulation of scattering processes, like the beta decay you can see here on the side. To make these computationable, these are often put on lattices, and then hope to predict physical phenomena, like the running of the coupling constants, the emergence of different phases, depending on the energy scale of the system, etc. We distinguish between 2 pillars in gauge theory. On the one hand, we have the abelian gauge series, Z2, U1. If you add matter to them, they become really interesting, have a lot of physical phenomena, have been widely studied by groups and companies also here in the audience. On the other hand, we have the non-abelian gauge theories, and they have not received so much attention, despite their relevance for the standard model, like the weak interaction being described by SU2. And for that reason, we will today focus really on that sector. And let me note that this is interesting even without matter being present. It's already an interacting, non-trivial theory. So we can study just the exchange particle in itself and ask questions like, how does it propagate through the vacuum? Which is described by the so-called two-point correlator function. Yeah? And this one depends on the vacuum. The vacuum is the ground state of an interactive Hamiltonian. Eigenstates is a hard task to compute them. And therefore, today we want to promote the use of the VQE, the variational quantum eigensolver, at least in the presence of gauge theories. Very briefly, Young-Mills theories, these are described by some Hamiltonian. Here, the Young-Mills Hamiltonian, two parts. On the one hand, you have the electric part, which acts on the edges of the lattice. And the second part is the plaquette part, which adds these gauge invariant excitations along the plaquettes of the Hamiltonian. Note, in contrast to Z2, on every edge, one cannot have only 0 and 1 as quantum numbers, but really any integer. And this bosonic nature makes things a bit more complicated and would require us to work with qudits or at least qubit registers and introduce some finite cutoff. Yeah. And of course, cutoff, that means we are sort of limited in the accuracy we can really hope to reach. Also, another complication is the presence of a constraint. And this constraint means that not all states in our Hilbert space are really physical, but only those which are sort of have this long-range entanglement, satisfying the Gauss constraint. So there's only a part in the Hilbert space that's really relevant, the so-called gauge invariant Hilbert space. And what we propose here today is, instead of simulating everything, let's simulate only this gauge invariant Hilbert space, or at least a small part larger than it, which has a few more states, but is easy simulatable, so-called spin network functions. Also, of course, we are not interested in just one vector in this Hilbert space. We are really interested in how this Hamiltonian depends on the coupling parameter, small g, and so a whole family of ground state vectors, depending on g running from 0 to infinity. Infinity is, of course, a bit hard to simulate on a computer, so we propose a compactification of this whole g space to 0 and 1. 0 meaning we have only this electrical part surviving within this new basis becomes diagonal. We can easily understand it. And at g equal 1, only the interacting plaquette part remains. All right, so this is our family of Hamiltonians. And we can now ask, can we use the VQE to sort of find the ground states and the ground state energies? VQE, very briefly, is the usual setting. We want to solve the eigenvalue equation. So let's start with a state we can easily prepare on our quantum computer, 0, 0, 0. Then we choose some algorithm ansatz parameterized by some parameters theta, and use this to create a state, psi theta. That state can now be used together with our Hamiltonian to evaluate the expectation value, corresponds to the energy in the system, and then we use a classical minimizer to sort of get this value as low as possible, and the minimal energy will mean that the state psi theta is equivalent to the ground state. Of course, works only if we have chosen a good ansatz, and this ansatz should therefore somehow be motivated by the Hamiltonian we are choosing. And to recall very briefly, there's of course a hardware-efficient ansatz, which has this very dense layers of C-naughts interwoven with dense layers of single qubit rotations, each with their own optimization parameter. And of course, this quickly runs into the bound plateau problem, many optimization parameters. We propose, therefore, today to replace it by a different ansatz, which is a bit less dense, has a bit more complicated multi-qubit gates, but also far fewer optimization parameters. So hopefully has an advantage in terms of scaling. Note, every link on the lattice, J, is represented by several qubits. Again, corresponding to some cutoff we have chosen, for example, third excited states, we can use 2 qubits to map all the states in there. And then if we do that, we can really give a concrete meaning to these building blocks given here, such that they always pump gauge invariant excitations into our system, therefore really creating states in the gauge invariant Hilbert space. All right, so far the setup. Let me re-emphasize this quickly. What is the main claim? We think there are some scaling prospects that VQEs can still have, at least for lattice gauge theories. Why? One, the Hamiltonian in our system is very local. Yeah? There's these small building blocks, and that means if you think about decomposing it into Pauli strings, that scales relatively mildly, and because the far apart terms commute, that means many of this can be parallelized, makes the readout parallelizable. If you think about scaling the lattice n to bigger and bigger lattice heights, that really we win with these kind of Hamiltonians in terms of scaling. Second, the Hamiltonian is also highly symmetric. You have translation, rotation invariance, and this also translates into the vacuum state, and this is good because enforcing these kind of symmetries, rotation symmetries and so on, means that we can reduce the number of optimization parameters we need. And also the short count can be reduced. One example would be the mean field ansatz in Z2, which really scales like 1, depending on the letter size. In a non-abelian setting, we cannot do that, but similar techniques make us hope that we also can get here the scaling down and far away from the whole letter size scaling. And the last part, the last argument, here especially, we propose to go directly to the gauge-invariant Hilbert space and states, and that will also help us both in reducing qubit numbers and optimization parameters counts. Very hand-wavy, we can even reduce up to 33% in terms of the qubit numbers needed. Okay, these are the claims. Now we want to see all of this in action, so on the remainder of the talk, we will look at a small toy model to see how this all plays out. And the toy model today is one vertex with 6 edges, so a 3-dimensional lattice. Think about a big lattice and we impose translational symmetry before we quantize it as a motivation. Then we go to the gauge-invariant Hilbert space, look there at the super selection sector which contains the ground state, and we find, upon a cutoff, we can describe it by 3 quantum numbers. Or with a cutoff then, 6 data qubits. And that's nice because this kind of system, of course, we can solve it classically, but we can also take the quantum computer to solve it and emulate it classically, really giving us access to see precisely how the VQ behaves in these settings. Looking again quickly at the Hamiltonian, right? We have this coupling parameter, and as we can see, okay, different values of G will correspond to different regimes in the theory, also known as phases. So G equals 0, I already mentioned this is only a diagonal Hamiltonian, so the whole theory is sort of free. But as we turn up G, we sort of expect that we create more correlations in the system. Yeah? And in order for the vacuum vector to describe these long-range correlations, we expect that there are more of these gauge-invariant excitations in the system. Our algorithm sort of pumps excitations into the system. That means we expect that we need longer and longer algorithms to describe theories with larger G values. So to visualize this quickly, imagine we have some algorithm that creates these excitations, and we create now some systematic states, these preparation algorithms, where we pump more and more excitations into the system. Those will, of course, be corresponding to sort of longer and longer and longer chains in this algorithm. We could, of course, take this further and further, needing then, of course, more 2-qubit gates, more optimization parameters. But crucially, if you compare this to the hardware-efficient ansatz, at a similar accuracy, we require far fewer numbers of optimization parameters, of course, at the cost of more 2-qubit gate counts. But still, we see that there's, in scaling, then at some point, an advantage reached. Now, we can, of course, simulate all of that in an ideal setting first and look at the overlap with the exact solution. Yeah, so we see the error that remains. And according to the claim, if we take deeper and deeper and deeper algorithms, 2, 3, 4, those become better and better in the large G regime. And in the small G regime, they all perform really, really well. So this is nice results. But of course, this is the overlap with the exact state. To that, we don't really have access in a normal setting. So let's look quickly at the energy. So this is really the energy of the ground state, which you would typically get from the measurements. And we see there's this exact solution. Whoops. And there's a certain uncertainty coming from this cutoff, telling us that we cannot really be sure with our cutoff what the value should be. And also here we see that the deeper algorithms, especially in this large G regime, perform increasingly better. Of course, this is ideal setting. In real quantum devices, we have noise, and noise is a bit of a, there's antagonistic influence, right? We see deeper algorithms perform better, but of course, they would also be prone to more noise. So there's a bit of a trade-off. To make an example, we now focus on the sort of middle length algorithm, which pumps 3 excitations into the system. And we want to emulate it with Markovian noise, inspired from really 2-qubit gates on a superconducting quantum computer with squared topology, CZ gates with 0.5% error. So realistic parameters, and in simulations we get, okay, we lose, of course, a lot of predictability power. Sure, but there's no error mitigation done yet. So if we add this and do only very small, simple error mitigation, like we project back to the gauge-invariant states at the end, or we think about some symmetries in the system, like they should all be rotational invariant, we get with our values really very, very close back to the ideal results. So this is nice. We have really a strong predictability power here. OK, so this tells us we can really create the ground state. But can we do now something with this? Well, if you remember, the whole thing started out with me saying, hey, an interesting quantity would be the two-point correlator in the system. And now, knowing how to prepare the ground state, we can, of course, prepare the ground state in the emulator, and then really look at the two-point correlator function and see how this works out. And also here we see, although not always matching the analytic exact results, we can clearly see there's a conceptual free phase, which is uncorrelated, a strongly correlated phase, and interestingly, the phase transition really sharp and also qualitatively described with a suitable accuracy. So, to summarize, today I propose to you, yeah, one can still use VQE methods in lattice gauge theories, especially when we implement the Gauss constraint directly. That helps in reduction of qubit parameters, qubit numbers, optimization parameters, makes this feasible. We looked at a small toy model and studied this in an ideal and a noisy environment and saw that physical properties like these phase transitions can be really obtained with suitable accuracy. Now, next steps. Once our quantum computing devices in our labs become online, soon a 17-qubit chip is operational, we look forward to really implement this on the devices, then with more advanced error mitigation schemes, more sophisticated parameter optimizers, and then, of course, eventually extend all of that to larger lattice sizes and include matter and all of that. And with that, I thank the team at the WMI and you for listening.
Great. Thank you very much, Klaus. Do we have any questions from the audience? Oh, sorry.
Thank you very much for this nice talk. I may have missed it, but if you can clarify a little bit, like how do you basically like ensure that your Hilbert space is like the physical one, so where like you have the gauge invariance? Are you doing any gauge fixing, or I don't know?
Yeah, I glossed over a bit. There is a formulation in which you can write a basis for your Hilbert space, which is very good adapted to gauge invariant states. This basis is the spin network basis. I can tell you more details about it. And we basically use this basis and don't even simulate the states which are outside of this basis. So there are only a few states in the spin networks remaining which are not gauge invariant, and we can really track those and do post-selection at the end to really identify those states and throw them out again when. So that answers the question.
Yeah.
Okay. Any other questions from the audience? Yeah, otherwise, I have a question. You kind of answered it towards the end, so thank you for stealing my question. But with the two-point correlators, maybe to kind of switch it up a little bit more, you've shown phase transitions. Do you see the VQE algorithm as a way of being able to actually probe and understand maybe qualitative physics over quantitative physics for maybe things that are harder to access classically in simulation, like the transition between, say, confinement versus like an asymptotic freedom type regime and some kind of bound pair or something like that?
Yeah.
I think the answer is yes.
Exactly. So, yeah, you said it already. I mean, this is the kind of things we are really looking forward to, right? Not necessarily being able to precise with the utmost accuracy what is the value of the correlator, but really tell us, especially if you have more, I mean, this is one degree of freedom at the moment is one coupling strength, but once you have matter, you have also the strength of the matter coupling to it. This comes into the confinement. And then really the interplay of these parameters becomes interesting. And then to really see accurately at which point you transition from one to the other phase is sort of the goal that we want to probe, because that tells us, are you in the confined regime or not with your theories? If you do renormalization, these coupling constants will change, and you're sort of looking for the critical points where they change, and all of that can be then probed with the VQE.
I guess maybe a follow-up on this. We are talking about the context of a VQE regime to be able to maybe find some parameter space. Can you envision maybe the solutions of this VQE algorithm and finding some ground state being then used as an input to some kind of Trotter algorithm to actually explore dynamics and things?
I mean, yeah, that is of course not something which I envision, but that has already been done a lot, right? I mean, many papers, especially in the Z2 theory, which is more easy in quotation mark, more associated to qubits because it only has 0-1 states. There, people have already added matter and really look at this kind of creating an input state, mean field ansatz, for example, very easy, small VQE, and then trotterize the system on that. And we provide the same basic building blocks now for the more physical relevant gauge systems, interaction strings.
Yeah. would you please help me thank Klaus again for his fantastic talk?
Thank you a lot.
And our final speaker for today is Roberto Moretti from University of Milan, Bicocca. I hope I'm pronouncing it correctly. And today he's going to be talking about parallelizing commercial quantum hardware for feature encoding optimization in neutrino physics.
So, good afternoon, everyone. First of all, I would like to thank the organizer of the conference for really this beautiful conference and also to give me the opportunity to contribute in this session. This talk is going to be about a real-world application case using parallelized NISQ hardware, and in particular, the use case is about neutrino physics. Neutrino physics is a very fascinating particle within the standard model. And in particular, in the experiments we were analyzing, we focused on the search of a very exotic decay, which is the neutrinoless double beta decay, in which, well, normally a double beta decay occurs when there is an emission of, let's see, yeah, of 2 electrons in the final state and then 2 neutrinos. In this case, the 2 neutrinos annihilate. Demonstrating that this decay exists will give us a lot of insights on neutrino physics, such as concluding that they are Majorana particles and that there are lepton number violating processes. So the task we had to solve using quantum computing was binary classification. So implementing machine learning for binary classification, trying to understand if there were some advantages with respect to traditional methods. The experiment leverages a liquid argon time projection chamber, which is a type of detector that is able to reconstruct 3-dimensionally the track produced by the charged particles in the final state. So what we wanted to do was to create a machine learning classifier to distinguish between our signal topology, the double beta, and one of the most dangerous background, which is a single beta topology. So distinguishing between 2 electrons ranging from the same point in space and 1 single electron just appearing inside the active volume of the detector. We actually, in a past study, we tried to use transformers and convolutional neural networks on a relatively big data set to make the classification, reaching about 76% accuracy, which is still not very high. So we expect this classification problem to be hard, also for quantum. So for NISQ, we know that we usually don't like to work with many features. We had 76 features in total to begin with, which corresponded to the voxel constituted the 3D tracks. And so we reduced this number down to 18 features with a very low loss and in a label agnostic way using an autoencoder, so a feed-forward layer from which we could extract a latent space representation of the initial features into 18. As you can see here from some univariate distributions here, just 2 examples, not always these features are, let's say, well behaved. They seem to be sometimes irregular and creating this multi-modal peak behavior. And also the overlap between classes is really massive. So this also corroborates the fact that it's going to be a challenging classification task. The algorithm we used was the quantum support vector machine, which I believe many of you are really familiar with. We used the standard formalization of the quantum kernel, so the staked vector quantum kernel. And as you know, one of the advantages of QSVMs is that they usually lead to very expressive classifiers because the implicit quantum feature map that is defined when we write down a quantum kernel lives in a Hilbert space that grows exponentially with the number of qubits. So a really expressive classifier, although a bit prone to overfitting. A disadvantage, though, is that there's no recipe telling us what does this U operator looks like in terms of gate content. So what's the best quantum feature map for our dataset? Often, many studies involve using heuristic feature map embedding. What we tried to do here was to use a meta-heuristic approach based on genetic algorithm. Genetic algorithms are a class of gradient-free optimizer, so very useful in this case since we want to optimize some complex structures not differentiable, in particular the gate content of quantum circuits, basically. And it is based on an iterative process where we first define random generations of quantum kernel. We encode it in terms of some gene content, integer numbers, basically, in a string. And through operations of mutation and crossover, this population iteratively improves, at least according to some way we used to evaluate them, called fitness function. Engineering the fitness function is very important. We tried two approaches using 3 metrics in total. We tried a mono-objective approach, which was just, the fitness function was just a linear combination, weighted combination of the accuracy and classification on a cross-validated fold, and the sigma parameter, which is the standard deviation of the off-diagonal elements of the kernel matrices. This is a very important parameter, so we want it to be high, because it alleviates a bit the problem of exponential concentration, which is a bit of like the equivalent of barren plateaus for QSVMs. We also tried a multi-objective approach, in which we tried to optimize using Pareto-from techniques and NSGA2 algorithm, the accuracy in classification, and at the same time minimize the transpile depth of the feature map, assuming some native gates of a QPU and some connectivities. So we ran some tests on a state vector, so completely an ideal classical simulation, just to prove that this algorithm indeed works. We see how the fitness functions improve. At first, it improves rapidly, and then it tends to plateau as the number of generation increases. A nice result I wanted to point out is that you can see here these dashed vertical lines in the both plots. This goes down to the best accuracy we could achieve with a classical SVMs from, let's say, the typical feature map. In particular, this is the Gaussian kernel from the scikit-learn library. So this is a very nice example on how at least quantum-inspired approach can sometimes surpass, in terms of performances, some standard out-of-the-box classical models. So finally, we come to the idea of our work, which is nice. One day, we would like to optimize quantum feature map directly on quantum hardware, because we want to be able to compute classically intractable feature maps technically. So the question was, can we do this today on NISQ hardware? So not so many qubits and also some error occurring. And can we do this in a parallelized fashion, basically to save money on cloud access to quantum companies? Is it feasible, or does the noise overwhelms, let's say, the thickness function, natural fluctuations, and for, let's say, making it possible to have a genetic optimization overall? So we didn't have enough runtime on any QPU to actually run genetic optimization from start to finish. We tried to address a simpler question, but still very insightful. Can we partition 100 plus qubits devices into several subunits and use them to compute the same identical quantum kernel with like enough precision? So what we did here was to identify subpartition of length 4, so 4 qubits in a chain topology where the connectivities, at least from the tested device Nazca in Brisbane, which had a preferential direction in the equal cross resonance to qubit gate, and the direction was right, left, or equivalently left, right. We also tried, of course, to avoid some region that was, like at the time, was reporting maybe low performance in terms of readout and gate errors. So by running at the same time a big circuit, so coherently computing many copies of the same quantum kernels, we were able to rank, to quantify the goodness of each of our subpartition. For example, this histogram select just one couple inside our dataset, so one element in the kernel matrix. And for each element, we can draw some distribution where each entry is computed by a different subpartition in the QPU. And so we can just calculate the standard deviation of this distribution, and also how much is it far from the state vector kernel. This was the quantum circuit that was used, so for 2 cubic gates, for 2 cubic gates, and like rather simple, we could say, but at least now we were able to rank each subpartition based on the Frobenius norm of the difference between the state vector matrix and the real matrix. And for example, if we rule out the worst 5 subpartition out of about 20 in each QPU, we see how the spreads on average tends to be much smaller, and also the spread distribution is much narrower. We can also progressively rule out from the worst to the best the subpartitions to see how the average spread reduces. Obviously, from this data-driven results, we could see that this spread amounts to like a maximum of around 0.07 for the worst device, and goes down to around 0.01 when we keep only the 2 best partitions. So we use this data to go back to the original question: can we run this genetic optimization at least on 4 qubits and with this kind of error budget? We came back to the state vector and then added some Gaussian noise on the kernel matrix directly with a spread, with a standard deviation for the Gaussian from 0, so no noise, to roughly 0.05. So more or less where we are with data. And we see how the genetic optimization can start, begins to be visible at about 0.02, but is definitely visible already at 0.01, which corresponds to keeping the best 20% partitions in these QPUs. So to conclude, from the point of view of neutrino physics, unfortunately there is nothing much to say. The accuracy for this classification task is too low. We were below 70% with this approach, so this cannot yet be used by particle physicists to run analysis. But from the point of view of, say, quantum computing, NISQ quantum computing, we found a nice applications with some very encouraging results, telling us that we can indeed parallelize hardware, quantum hardware now with already available devices. And also, we didn't even use the best QPU at the moment. We used Nazca, Brisbane, and Torino. And we also didn't use any quantum mitigation strategies, and of course, no error correction. So there is still room for improvement, and we are looking forward to study more about this. So if you want to know more quantitative details about all this study, you can scan the QR code for our last paper. Thank you very much for your attention.
Great, thank you very much, Roberto. Do we have any questions from the audience? I had a question, kind of following up on this last point you made about how you're just not quite at the level of hardware that would give you an advantage. Do you have any idea of what you would need from a hardware to be able to do something kind of more interesting or more state-of-the-art?
Well, so far, it actually seems to be that we could also just simply improve our method first between understanding how can the hardware get better. For example, we choose a rather arbitrary subpartition logic. This could maybe be better. I would suggest that maybe more advanced transpiling techniques of the overall quantum circuits can extract something that is equivalent to 20 of the same quantum kernels at the same time. This could give us a little bit of of an improvement already. For the point of view of QPUs, it really seems like it's true we are not quite there, but it seems like already we can have some sort of parallelization already. So I would say that any kind of improvement at this point could really help us lowering the threshold for this kind of optimization. Yeah.
Great, thank you. Are there any more questions or anything? Oh, one in the middle. Oh. watch up. Nice catch.
Thank you very much for a great talk. You briefly brought into it the question of how you make a good a feature map on a quantum computer. And since you're more into the domain than I am, I would just like to hear what experiences have you now made? What should I think about when I try to make a good kernel map such that I can use a quantum computer to do machine learning instead of using a classical computer? Very general question. It's just now you're an expert, you did an experiment on this. What should I think about in the future? Yeah,
Okay, that's a good question. I believe what I think many of the field also think that QSVMs can be extremely expressive and sometimes too much, meaning that then you are really aggressively overfit. I really found QSVMs that were doing really great on the training set, and then on the validation, they're completely random. Already with where none of the classical approach actually have this kind of problem, at least not in this magnitude. For the future, yeah, I think this is a bit of the point, because we need to find nice way. This was kind of a brute force meta heuristic, but we need to really optimize our techniques to find a suitable feature map. That also thinking about when we will use more qubits, we overfit even more. I would say that this is still very challenging, and I don't really have a precise answer for what we should expect. From the point of view of having really intricate data set, I am very actually optimistic about the use of general QSVMs because of the expressiveness, basically. So with large amount of data, this should be, like, the overfitting should be progressively mitigated. This kind of a hope at this point, more than an answer, but thanks.
Thank you.
Great. I think that's it for the session. Thank you very much, Roberto.
Thanks.
It was a really excellent talk.
Great. Then we are at the end of the scientific sessions for today. The next step on the program is we will have some excursions. You all signed up, and to give you a little bit more details about exactly where you need to go and what you need to do when you go there, Amber will take over.
Thank you very much. I get to share the most fun part again, logistical details. So it is now about 5:30, and I should share with you that at 5:30, so straight away after the session, the people that have signed up for one of 4 excursions, they're listed there, should go to 4 different places to gather with the group that will then head over to the specific excursions. The 4 are at QTech, to go to the campus in the QTech building, please assemble at the QTech booth, right outside to the right. You'll be counted, and then they know how many people to expect. The House of Quantum has 2 places that can be visited. One is EW10, which shows Orange QS and Quantware, for example. And one is the House of Quantum DT01 is for Q-blocks. They will have a lab launch and also drinks and bites afterwards. For the House of Quantum EW10 tour, the first one, please assemble at the Moods Summer Terrace, so that's outside the venue. And for the Q-blocks tour, House of Quantum DT01, go to the Q-blocks booth. For the boat tour, which is supported by Zurich Instruments, please go to the Zurich Instruments booth. So that all hopefully makes sense. Some extra information, if you didn't sign up for a tour and you still would like to join one of them, it is most difficult to join the QTech and the Zurich Instruments side events because they are really capacity limited. So the boat tour and the visit to QTech, you can still try. When they do the head count and you really want to join, you can ask for a favor. Probably easiest to head over to the Q-blocks booth or the Moods Summer Terrace for the Q-blocks tour for the House of Quantum visits, basically. That's where the most space is still available. For transportation, some people that would have to go by foot, this will be explained at the place where you all collect, how to do that best. Then after the tours, officially the program ends now, the SQA program, and the side events take over. But after the tours, there are 2 tips I wanted to give with you. There are some special dinners arranged. And if you are not invited to any of those and you still look for a place to eat, you can consider the SQA menu at Moods. I heard from them yesterday that there were 12 tables from SQA attendees, so they were very happy with that, and I hope you were happy with the food there. And the other alternative is Qublox has indicated that you would also still be welcome after your excursions to join at the Qublox building where they launched their new lab for drinks and bites for free. Then. And I think that's all I wanted to share. So enjoy your evening, enjoy the excursions, and have a nice evening.